Griffith University. I'm in Brisbane, Australia.
Okay.
So it's afternoon, as you see with the sun.
Welcome.
Yes, I guess I will mute now. I guess we're starting.
Yeah. Professor Anil Kumar, good morning.
That one mute.
Yeah, Professor Anil Kumar, good morning.
Good morning.
Yeah.
Good morning.
Yeah, good morning.
Prashant, how are you?
Fine, so far. So far, fine. I hope you all are fine. Yeah, I think we can start. Niranjana.
Should we start?
Yeah.
I'm fine.
Okay.
Maybe you can wait 1 or 2 minutes. 9:59 only. So maybe
Okay,
1 or 2 minutes.
Yeah. Okay.
Yes, it's just hit 10, so I think maybe a couple of more minutes. So let me know when we should start.
See, now you can start anytime you want.
All right. All right. So good morning, everybody, at least those who are from India, and good afternoon, Professor Wiseman. And I guess for some people it could be good evening as well. So welcome, everybody. It's my great pleasure and privilege to be able to actually handle the very first session on the School on Quantum Information and Quantum Technology hosted at IISER Kolkata this year. And this, as I understand, I'm no expert in this domain, but this is, a very upcoming domain. And I think, those of us who are in the numerical sciences, there's a lot that we can learn and try to incorporate into our own research, I feel. So thank you, Professor Panigrahi, for allowing me to handle the first session. And I request you to say a few words to orient everybody in this session. Professor Panigrahi.
So thank you, Niranjana. And good morning good evening to all of you. First of all, I know there are people who are distributed in space and time. So it may be inconvenient for some of you, but wherever you are, please take care of your health, do some exercise, keep yourself fit, and stay safe. So this is the second version of this quantum information, quantum technology, which started in 2019. So many of the speakers of today and many students who are TA, teaching assistants like Shreya and others, they were all veterans. They were there in 2019. And you can see the good effect of that school that it has produced to Shreya Banerjee, who is a PhD, Sharmila from IIT Madras, who is already a tutor. And many students have picked up this IBM platform quite well. And because of them, we took this initiative. When I mentioned this to Professor Pal, he was very encouraging and he said, it's such a good thing, let's proceed. Now this time, because of this online platform, it has both good and bad effect. So physically, you are not here to enjoy the greenery of our campus, but large number of students could register from sitting anywhere, and many of them are from outside also. And again, we have gotten very good speakers from abroad, also in India, thanks to this pandemic situation where people could access, they are not traveling much. So you will have a great success in hearing good things from all over the world. Now, first of all, this quantum information, quantum technology is now, as Niranjana pointed out, is becoming the focus area. There are enormous number of programs. Government of India itself has announced specific budget. There is a roadmap which is being created, and some of these people like Urvashi and others who are there, and they have actively participating in this, making the roadmap. Quite many of them are here. You will hear from many of them. And you Quest, quantum-inspired, quantum-enabled science and technology is a program of GST, spearheaded by ACRB, and already money has come to many researchers, and more is on the pipeline. In addition, there are many specific targeted projects going on in the quantum technology. So Niti Aayog, Dr. Saraswat, is spearheading this thing, taking active initiative. So there is, this quantum has come there. You may ask why so long? See, by 1925, quantum theory was well developed. Dirac's book of 1932 has almost everything what we know so far. But quantum theory produced many paradoxes, starting from EPR, so-called EPR paradox. But when engineers came in, they made it a reality. For example, the same EPR paradox was used to teleport. And then experimental things come in. Late 90s, experiments started coming, and the Grover's algorithm, the very powerful search algorithm, then the algorithm to break secret codes by Peter Shor, that made it mainstream. And since the last few years, it has really become mainstream. And IBM has played a very strong role because they have the quantum computer from early on, give free access. Sitting here in Mohanpur, we could do a lot of things. And you can do really get access, and they're very patient with you. For example, this time when we requested them, Dr. Guha from California delegated this to Kylie, and our Shreya is coordinating it. They have identified 5 key researchers to give us hands-on training starting from July 4th. I'm really thankful to them. Now, due to Shreya's effort, Ericsson is here because Shreya did a project there with Ericsson. They are also into quantum technology. TCS is here. On their own, they have contacted us. And QNew Lab, Anita Banerjee, she is here. So you can see there are startups, private companies coming up in this area, taking active interest in academics, offering projects. For example, our ISO Kolkata student, Rahul Pratap Singh, he's spearheading this IBM's effort to popularize QSKit. So he's basically the spokesperson for India. And in the process, he's studying and making money also, getting fellowship. Now you will realize this quantum computation, quantum technology has come a long way. Both theorists and experimentalists have played a key role. For example, in this session, you'll find Professor Dipankar Home, then Professor Ghosh, and Guru Prasad Kaur, who are the only pioneers in educating many Indians about the subtle aspects of quantum mechanics and quantum information theory. And experiment, Professor Anil Kumar, the veteran person who has trained a generation of NMR people, who really brought quantum computation experiment to India. All of his students are occupying ISO Kolkata, ISO Mohali, ISO Pune, TIFR, and whatnot. And, for example, similarly, I only remember Professor Rajgopal, A.K. Rajgopal, then Professor K.R. Parthasarathi, who are so enthusiastic. They are not able to give talks, but they have persuaded Usha Devi to give talks on their behalf. So that is the enthusiasm of the India. And young people, and it's a subject which is meant for class 12 students onwards to anybody. So for example, you may think class 12 students, what he or she can do. Please check up this girl, Ewin Tang, E-W-I-N-T-A-N-G, class 12 student doing a project in Texas, could solve a very outstanding problem. A computer science and mathematician oriented person, could solve the so-called quantum validation problem. Urmila Mahadev, after 8 years, one paper, computer science background. So many people from different kind of backgrounds are contributing and making a difference. So believe it or not, although quantum theory is understood, but making it technology has enormous challenge. So thanks to many of these students who are now there as tutors and spearheading program from all over India, Sabhyata, Gargi, Sarmila, and number of them. So they are the veterans of last time. From this time also, I'm pretty sure many veterans will be produced. And I specifically thank IBM for taking a great initiative in training our students and training students all over India. I think they have a program and making their computers accessible to us. So I think with this, I would welcome all of you and hope that you will enjoy the session. And Nilandana, now please take on.
Thank you so much, Professor Panigrahi, to giving us a very nice and succinct overview of the scope of quantum information and technology. I mean, there's so much going on here in ICER and also elsewhere all across the world, and I think different kinds of people need to come and join hands. So we have, of course, a very diverse set of faculty here, and I request Professor Ananda Dasgupta, who's currently the chair of the Department of Physical Sciences at ISO Kolkata, to actually give us his perspective on the workshop or his views about the Physical Sciences Department. Professor Dasgupta?
Thank you, Nilanjana. Let me just give me some time before I can just share my slide.
Of course.
Finding it a bit difficult to locate the actual slide I want to share right now. Okay, I think I've got it. Okay. Let's see. Can you see?
It's
Or I
visible.
think I've got the wrong slide.
The slides were visible. You just need to go full screen. Something was visible.
Okay, I just hope I got the right one. Just check.
Yeah, Ananda, what time are you going to start?
Hello? I couldn't hear you.
Okay.
So is the slide visible now? Small version at least?
They are visible. Could you go full screen, please? Then it would be
I will.
easier on the eyes.
So now?
No, slideshow maybe? Yeah, perfect. Yeah.
Okay.
Please go ahead.
Okay. Good morning, everybody, or good afternoon or good evening, whatever may be the time zone that you are in. I have this very pleasant duty of introducing the department as a sort of prelude to this wonderful workshop that we are going to have. Well, it's also a bit of a daunting task because, as you all know, the department is a lot more than just a few numbers or even a few pictures. So under ideal situations, you would all have been here, at least in campus, enjoying the department, interacting with people. Unfortunately, in the current situation, as you are, well, this is just not possible. So I will begin with a sort of happier picture of a kind of gathering we used to have. Say this was in 2018, our DPS Day celebrations. And we had most of the people whom you see in this picture are department members, except for the director who is right in the front and a few external speakers who were invited for that day. But this is the kind of, well, festive atmosphere that we all long for nowadays. But since I cannot really convey that feeling to you, I will just give you a few numbers to tell you about what the department is like at present. So we have 31 faculty members, 271 students, and 9 support staff as of now. What is more important right now is that number of students is growing day by day. So basically, we have 170 BS/MS students, master students in our department, 33 integrated PhD students who have joined the PhD program, and 68 PhD students. As of now, these numbers are going to go up soon because we have had our PhD recruitment interviews this year. But this gives you a rough idea about our demographics. Okay, this is the teaching program that we have. I'm not going to go through the full details of this, but from the slide, you should be able to see that we have a rather diverse teaching program. We teach different kinds of subjects. Of course, basic core physics subjects, as well as quite a few interdisciplinary subjects. And what is, of course, very interesting for us is that our students have performed spectacularly in different places. We have had Rhodes Scholars, SPM scholarship holders. Students have been placed in Princeton, Caltech, Stanford, IISc, TIFR, lots of other places. And let me just quickly stress that in DPS, when we consider teaching, we lay strong emphasis on the foundations of physics early on, and then we provide a diversity of advanced courses. And this roughly is the division of our faculty members, the 31 of us, among subjects, although frankly, there's a lot of overlap. So there are people who work in multiple disciplines. So this is just a rough guide of how things go in our department. So for example, you will see that quantum information theory, optics, spectroscopy counts 7 people, which is quite a strong number in the context of 31 strong department. And that is, of course, the focus theme of this particular workshop. Some numbers quickly, just to illustrate what kind of research we do. Since inception, which was in 2006, the department has published around 1,100 papers and total H index of 57. But of course, we had a very small department to begin with, and then we grew slowly. So just to put this in context, the last 2 years, 2018 to 2020, we have had 485 publications with an H index of 24, average citations of above 9 per paper, which is quite good, I would say. And just to illustrate how the pandemic has affected or not really affected us, the publication count in 2020 was slightly smaller, just by one actually, than that of 2019. We did not grow as we did in the previous years, but that was perhaps more because of the lockdown and other features, things that we all had to endure. Okay, this is not really very relevant right now. Our faculty have won all kinds of awards and honors. We have had Fellow of the World Academy of Sciences. We have, okay, I'm not going to go through the whole list here. This is a long list. But let me mention things like recent awards like G.G. Stokes Award in optical polarization to Nirmal Ghosh, who was the first Indian recipient of this award. We have had lots more. So I'm not going to read all of that. But let me just conclude with this. This is our logo from our 10-year celebration a while back. This was after the GPS department proper was formed. That has been 2 years now, or 3 years actually, to be more precise. And the spaceship that we sort of used as a background image is sort of indicative of how we want to really move forward. At present, we are well on the way, but frankly, there's a long way still to go. So with that, I would want to end my presentation and give it over to you, Nilanjana.
Okay, thank you, Professor Dasgupta. Thank you very much for that nice overview. So I'll move on to the next phase, and I will request Professor Saurabh Pal, who I'll have the privilege of introducing just a bit later formally for his talk. But, I would request him to say some words about our institute in general and about the QIQT workshop in particular. His perspective, please. Professor Pal.
Thank you. Thank you, Nilanjana. Am I audible?
Yes, you're audible. So I just got feedback from Shahid saying that all of this is being shown up in YouTube, and we have nearly 500 participants over there. So in general, I request the speakers to be a little loud because it's, apparently, some of it is getting lost in translation when it's going over to YouTube. So, but I think you're fine. I think you're fine, Professor Pal. Please go ahead.
Okay. Yeah. Okay, Nilanjana. Is it okay now? Little better?
Yeah, it sounds good. Yeah. It sounds good.
Okay. So thank you. Indeed, I will have an opportunity to speak the topic a little bit later. But at this point, during the inauguration, I want to speak a little bit about what we are doing, QIQT and the Institute. I have to first thank, of course, Professor Panigrahi for putting together this wonderful workshop spanning over a few weeks. And this is not very easy job to do online. And of course, we are forced to do online. In fact, when he first suggested, quite some time back, we had even a hope that it could be a kind of physical meeting, at least a hybrid meeting. But eventually, things became bad to worse, at least in Indian context, with the second wave coming in, as all of you know. And we obviously abandoned that plan, and we are fully online. So I'm very happy to welcome all the participants and any other guests who are in the YouTube, online, and of course in the Zoom. All of you who are here, the panelists and the volunteers, it's a welcome to the beginning of this workshop. So I'm very happy to first inaugurate the QIQT workshop. I think it's a very important workshop, and I can see that there are people who are joining in from all over the world. I'm happy to welcome particularly our guests from abroad and all from India. It's a great opportunity simply because quantum information and quantum technology has become very, very important. In fact, I'm going to highlight on how important it is for certain branches of chemistry and physics and biology, of course. And we are one of the primary customers of quantum computers. We can be potentially a primary customer of quantum computers because of the power that it will give us. So to say a few words, I am a computational chemist. I am actually a theoretical chemist who turned over to computational chemistry more and more in recent days while continuing to do theory. However, great advances of theory, as all of you know, must be complemented by advances in computers. Not only the technology, not only the hardware, but also the software, the computer software, algorithm, but the hardware is very, very important. The speed that we require to solve the problem. In fact, I would quote the very famous problem, the statement of Dirac, when he said in 1929 that apparently all the problems are solved because of the Schrodinger equation, because of quantum mechanics, except that we can't really solve them because we don't have computers. We are limited by computers. And that is where quantum computing is going to change the scenario. And I think it is going to transform the space of chemistry, physics, biology, engineering, and all of sciences, art science, geology, because we can do so much more modeling and simulations. There's such powerful simulations that I think it will transform. And that is a fond hope with which I'm going to begin my lecture when I come to the technical lecture, of course. But the point is, we have not reached there. We're very far from reaching there. And I think there are experts who will tell us how far we are. I am not an expert on quantum computing per se. I, of course, am a person of quantum mechanics who applies approximate quantum mechanics, who develops theory for chemical problems, and then also applies. So to that extent, I said we can be very good customers of quantum computers when they come. And there are several like that, not just me, all of chemistry, physics, biology, and engineering, art science, many people who of course, depend on mathematical methods, algorithms, and so on. So I think in that sense, this workshop is extremely important. It's a very topical subject, and I'm very happy that so many people from all over the world have joined. And I look at the program is extremely rich. So at the very outset, I must thank all the speakers, all the participants from abroad, from India, for joining in for this online workshop. Professor Panigrahi, for very special thanks to him for putting together this program, and of course his team. Nothing can be done without the team of volunteers who have worked with him tirelessly. I have seen him, how much engaged he has been over the years, over the months and weeks on quantum information and quantum technology. And of course, over the years, since I have seen him, he has been speaking about it. The QI quantum information as a very important subject. He has submitted projects and so on. So I think my deep thanks, deep appreciation to whatever he is doing. And there are other people like Professor Chiranjeev Mitra, who's also there in the Zoom, and several other within the ICER who are trying to push this subject. The subject is very important to all of us. And we are really watching very hopefully how far we can move. I mean, that is very, very important from the sidelines. And of course, being a person with a knowledge of quantum mechanics, we understand how it is going to move in a very broad manner. I also have to say that thanks to DST, SERB, several other agencies, and as Professor Panigrahi said, to Professor Saraswati, who actually conceived many of these ideas in the Niti Aayog. I think there have been a lot of discussion. I remember in last October, Government of India organized with the DRDO a program called Vaibhav. Professor Panigrahi will recall, and many of us will recall, who are here, Vaibhav program, and I was actually leading the computational chemistry, computational science in general. And I could see that there's a very separate focus on quantum computers, separate sessions on quantum computers. So I think it is very, very important that the quantum computers have been recognized by the Government of India. And I hope under the Vaibhav scheme, also certain progress takes place in very near future. So I think Saraswati played a very important role in the Niti Aayog. In fact, Professor Ashutosh Sharma, DST secretary, actually, we invited him for the inauguration, but because of his time, he could not come actually. He has been preoccupied, but he has very kindly given a message message of good wishes and goodwill for this symposium, so that he wishes the symposium great success. So I think there are people who all over the world, all over the funding agencies who want this kind of conferences to be successful. SERB Secretary also, Sandeep Verma, Sarasat ji, all of them. So I'm very happy that the government is also engaged. The government of India is also engaged, as many other governments. So wishing this conference great success, I would now like to highlight in last few minutes about my institute. Of course, for those, the institute is on the website. So anybody who likes to have more details can actually go to the website and look at the institute profile. So I don't need to give too much details, but Professor Ananda Dasgupta already spoke about the physics department. I should say, apart from the physics, we have the chemistry, we have biology, we have art science, which also include art and environment science in some sense, parts of geology, and of course the mathematics and statistics, which is very, very important. Mathematical and statistical sciences. So these are the 5 primary departments in which we give degree at this point of time. Degree, which I call undergraduate degree, BSMS, which is our flagship degree. In addition to that, we have a PhD program, which is basically, as Professor Dasgupta showed, integrated PhD, where people start after the bachelor's and continue to get PhD, and the normal PhD program, where people join after the master's and get PhD. So we have these 3 major programs and a little bit of 2-year MS program in certain areas, like in space science. In fact, we are looking at probably including having a 2-year master's program all across the institute, but that's for the future. I just thought that I would say that very recently we have started computational and data science. The name is computational and data science, not computer and data science. Computational and data science, as well as humanities and social sciences. So more likely in these 2 departments in near future, they will have PhD program. But at this point of time, they are also contributing to the master's program, BSMS program, by contributing the coursework. So I think these are the broad degrees in the departments that we have in the institute. We have 4 interdisciplinary centers of research where there are no additional faculty, but faculties from different departments are put together in different centers. And there are centers of high pressure, there are centers of environment, there are centers of space science, and there is a center of functional materials. So there are 4 centers which you have. We have also created a kind of virtual center for computational science, where a lot of people are working together. And I think there are lots of different things, including cloud computing, that we are going to explore in future in terms of computational science. Our institute, of course, was inaugurated in 2006, July, but we usually have the inauguration many times in August, because August is when when the classes start, end of July, August, classes start for the BSMS, the new batch starts. So 2006 to 2021, we are now completing 15 years of ICER, and 15 years is a kind of milestone. Like 10 years is a milestone, 15 years is a milestone. And I'm very happy, for example, Chemistry in Asian Journal is coming up with a special issue on the highlights of the work, of the research work, original research work by the faculties of ICER Kolkata, along with ICER Pune, which also came up at the same time in 2006. 2007, ICER Mohali came up. 2008, 2 more ICERs came up, ICER Bhopal and ICER Thiruvananthapuram. And very recently, more recently, I would say 2015, ICER Tirupati was established, and 2016, ICER Berhampur came up. So these are the 7 ICERs which you have spread over. Each ICER, of course, differs in the details. They have their own academic senate, they have a separate board of governors. So in many ways, they differ in the details. But I should say the general motto of all the ICERs is the same: to impart good science education in a holistic, interdisciplinary environment. And that is, I think, the main theme of all the ICERs. Do very high quality teaching, high quality research. And today the translation of scientific research has also become very, very important. So many ICERs are looking at setting up incubation center. So IISER Kolkata, I'm very happy to say that we have also an incubation center called RISE, and we have also one startup, and the second startup is likely to come very soon. So I think we are on our way to the translation of our science as required by the government today. So I hope the institute will continue to do well. Our students have done very well in terms of securing positions for PhD, postdoc, and even jobs now. Our faculties have won recognition awards from at the highest national level, and many of them even at the international level. And I think this is very good to see for a young institute. We get reasonable ranking. We are among the top 30, usually in the even top 25, sometimes in the NIRF ranking, National Institute ranking, which is quite good for an institution which came up in 2006, because many institutions who are above us, in fact, almost all institutions which are above us, came up much earlier than us. So I think compared to the institutions around the time that we came up, we are probably among the top 3 or 4. We also have very good ranking in the International Times Higher Education. In fact, very recently, our ranking has improved in last year, a significant margin. So I think we are there, and we hope to make not only national mark, but a global mark in near future. I think conference and workshops like this would go a long way in achieving our dreams, in fulfilling our dreams. Whatever happens will happen. I always say, Ke sara sara. But the dreams are those with which we live. And I think that is very, very important. We have high dreams, high hopes, and I'm sure with our very good faculty, and of course, a great number of students who are exceptionally qualified, we will do very well. Just to put numbers, we have about 125, 126 faculties on roll at this point of time, and we have about 1,900 odd BSMS students, 5 years, and more than 500 PhD students on the campus. And we have a few postdocs, so it's about 1,600 students that we have in the campus at this point of time. I mean, they're not in the campus, I'm sorry about that, because obviously now undergraduate classes are going online, but what I meant by on campus is that they're enrolled at IISER Kolkata. In the pandemic, of course, we had a lot of difficulty, but I think compared to many institutions, we have managed very well. Number of cases, number of active cases have been managed well. At this point, we have none inside the campus. We have also been able to continue our research, at least partially and many times completely during the pandemic for the PhD research. So I think that has been a great thing for us, and I hope this will actually translate in the institute going even higher in near future. With these few words, I would again thank Professor Panigrahi and his team, and I thank all the members, all the speakers in particular from abroad and from India. It's a long list. The tutorials, I'm sure the tutorials are going to be extremely important exercise, and I think they will be given due importance by all the tutorial managers as well as the participant. The tutorials are the heart of this kind of a workshop. And all the other participants. There are many who have registered, so I thank all of them from different parts and different time zones. I thank all of them for attending this workshop. And this is going to be a rich fare for next few weeks. Thank you very much, and thanks to all. It's impossible to name everybody. The physics department, of course, which has done a lot of work, because Professor Panigrahi belongs to the physics department. But I would say entire institute staff, the IT staff in particular, for making all the online things available. And of course, the entire staff who are involved from administration to IT and the faculty and the student volunteers, many students who are going to be there listening to these talks. Thanks to all of them. And I hope we'll have a good fair. With these few words, let me complete my inaugural talk, and I think I have a technical talk following this, which I hope I'll be able to give a reasonable account of why we require quantum computers. Thank you very much.
Thank you very much, Professor Pal. It was a fantastic overview of the scope of quantum computing, as well as, a nice overview of ICERs and ICER Kolkata in particular. So now I have the double privilege of introducing you as the very first speaker of this workshop. And yes, so that's, I'm going to formally introduce you. So introducing Professor Saurav Pal, well, I'm sure most of the audience is very familiar with Professor Saurav Pal here, but introducing him formally with all his accolades will take a lot of time. So I have tried to, condense the essential elements of it. Professor Pal got his integrated master's from IIT Kanpur in 1977, which was followed by a PhD at the Indian Association for the Cultivation of Sciences with Professor Debashish Mukherjee. And he went on to do his postdoc with Professor Rodney Bartlett at the University of Florida. And I think almost seamlessly from his postdoc, I mean, he didn't even, I guess, complete his postdoc formally, before which he joined as an independent scientist at the CSIR National Chemical Laboratory. And well, I'll come to his accolades and everything, but what I find personally fascinating about Professor Pal is that he contributed to fundamental developments of quantum chemistry, being in an actual chemical laboratory where he was surrounded by different kinds of experimentalists, of course, of the top kind. But he continued his passion in quantum chemistry for 3+ decades. And he did, he made seminal contributions from NCL. Well, I can't go over all of them, but, I will just mention that he made very fundamental contributions to the development of multi-reference coupled cluster in very different forms and fashions. And he went on to do several applications in material science after that. And, he has trained I think 2 generations of students. I know some of his students who are doing extremely well for themselves now. And, well, I thought I will also mention that many of his algorithms are now incorporated in, commercial quantum packages as well. Coming to his accolades, other than the fact that he's a member of many editorial boards of journals and societies, you can read up his website. In his list of honors, top down goes the Shanti Swarup Bhatnagar Award in the year 2000. It is treated a little bit as the equivalent of the Indian Nobel Prize, but that's the top award in India, scientific award. He's the recipient of the J.C. Bose National Fellowship. He's a recipient of the CRSI medals. He's a member of every national science society in India, and he's been decorated nationally and internationally. The list goes on. There are more than 24 entries into his list of accolades. But more than that, as I said, his contributions to quantum chemistry and his understanding of the theoretical sciences is vast. And what I have, I've personally known Professor Pal for about 12 years now, and what I'm fascinated is his ability to connect different kinds of quantitative sciences and, understand the broader picture in these details. So without further ado, I would request Professor Pal to come in again and deliver his lecture, which is for about an hour, Professor Pal, and the last 30 minutes are for questions. So I will try to continually take questions in the chat box, and in the last 30 minutes, I will present the questions to you. Professor Pal?
Thank you, Nilanjana, for excellent introduction. I will have to first share the screen, I suppose. So let me do that. Share screen. So just let me know if the screen is
okay.
Is it being shared?
Yes, it's it's coming out nicely. Please go to the full screen mode. That is.
Yeah, is it okay?
Yes, perfect.
Perfect.
Yes.
Is it moving?
Yes, the slides are moving.
Oh, that's great. Okay, that's great. Thank you, Nilanjana, for an excellent introduction. I must say that for those who do not know, I know Nilanjana for a very long time. She was also in NCL, and I must say that she is also a very passionate scientist. She also works on now computational biology. So I think I had a lot of interactions with her. She was at NCL, and I know her from now 2008, I think. So, so I thank you for your introduction. As I said, this workshop is an extremely important workshop. So I must thank the organizers of the workshop, Professor Panigrahi in particular, for inviting me to give the inaugural lecture, presumably because I'm director of IISER Kolkata, because I am not an expert of the quantum information. I know quantum mechanics, I'm a quantum chemist, but that doesn't mean that I know quantum information in great details. So I had initially great reservations, and I actually expressed that to Professor Panigrahi. But then I realized after talking to him that we are the people who are actually using computers and who require very high level computers to do our work. So in that sense, I think quantum computing is very important for us, and I agreed to give this inaugural lecture. So with that introduction, I have to say that I have put this title as a quantum mechanics as a foundation for multiscale simulation. And I think I'm going to come to the multiscale simulation, the scales at which people like Nilanjana are also working, some higher length scale. And there I'm going to emphasize that we need quantum computers. So I'm going to speak very little about quantum information in the middle of this thing. So I have divided my talk in 3 parts. I'm going to first talk about what do we do in computational chemistry and emphasize the need for a very high level computer. Then I'm going to talk a little bit about quantum computers, quantum information, how that can actually change the landscape. And then I'll go back to the kind of work that we are doing, some of my own research, and how all these can be value added by the quantum technology. So that is something that I'm going to speak over the course of next 1 hour. So if you have any questions, please write in the chat box. If you, of course, you can also ask me. Those who are in the Zoom, they can easily ask me. I'm not sure about YouTube, whether it is possible, but they can write in the chat box. And I think, I'm sure Nilanjana will put these questions to me. I have to say that while I was in NCL, I spent some time at IIT Bombay after my tenure at NCL Pune, before I actually came here. So that's the reason of this slide, which shows the 3 cities of Pune, Mumbai, and Kolkata, where I have done my work. Much of the work is, of course, moving from one place to another place. And Pune is where I, of course, did, as Nilanjana said, 3+ decades, to be precise, almost 33 years. I was in Pune. Just after my PhD, I actually joined NCL, and then I went for postdoc. So I think it was a good journey at the National Chemical Laboratory, where I felt initially quite threatened, I must say that, because the CSIR laboratories were for not only scientific, but also industrial research. And as you will see, I am doing quite a lot of the fundamental research, particularly at that time. But eventually, of course, I found that the CSIR also values, I must say that the value system has changed in this country. And today, as I said, from the government level, the quantum computing, quantum information, computational science, all these are put at a very high value. And I think that has been one of the greatest and the most rewarding experiences, if I have to say so, as I have gone forward in my life. I have already talked about IISER Kolkata, but just in case I miss it, I put that in this slide, that our emphasis is on interdisciplinary research and education, and we have become a brand, IISER. I must also put this slide. This is a very old slide. Many of you have seen many times, but this is a slide which is still very important, and today even more important as we are looking at quantum computing, that we must go to the high consideration of use with a high fundamental understanding, which is basically the Pasteur quadrant. And this is the use-inspired basic science. So that is what is actually captured by the Louis Pasteur. Many of us have, many people, not us, many people have actually gone to the pure basic research, but have not been able to transit to the posterior quadrant. Is this the right way to transit? Is this the way to transit? Go to the x-axis, then go to the y-axis, or is it a diagonal way that you can transit? I think this is something that the educators have to put a lot of thoughts on how to bring people from here, who are in the beginning here, to the posterior quadrant. That has been the big challenge all over the world. One of the things that people have felt that those who have done very fundamental science have not been able to translate, and today with quantum computers it is now possible, has been captured by a very famous statement by C.P. Snow as late as 1964, when he said, we prided ourselves that the science that we were doing could not in any conceivable circumstances have any practical use. Prided. More firmly one could make the claim, the more superior one felt. And so this has been the problem of many basic scientists globally I'm speaking, going into the translational science, going into the posterior quadrant. In terms of mathematics and computer, I think I just want to quote a very old quotation by Andre Quatele, which says the more progress physical sciences make, the more they tend to enter the domain of mathematics, which is a kind of center to which they all converge. We may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculation. So you can see the importance of the computers, importance of the mathematics in physical sciences was highlighted long back, 200 years before, even before quantum mechanics came. But what was the problem? And why did I say there have been problems, particularly in chemical labs? Look at this statement. A. Comte, 1830, 2 years after this statement, it says every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should ever hold a prominent place in chemistry, an aberration, which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. So you can imagine how mathematics was viewed in the context of chemistry. And that was a great challenge. But today, things have completely changed. Today, chemists understand the importance of mathematics, importance of computer. It's not the chemist, it's the biologist also, who understand the importance of computational biology. In fact, the chemistry started, I'll just skip this slide, with the G.N. Lewis, a very famous person of G.N. Lewis, who actually did the valence and the structure of atoms and molecules, and who defined physical chemistry as encompassing everything that is interesting. He actually talked of electron pair, and his very famous paper of 1916 of the atom and the molecule actually was extremely important, and it became very, very important. But G.N. Lewis did look at the bonding of molecules even before quantum mechanics came. He actually did not use quantum mechanics. He looked at an octet rule and started looking at how to do chemistry. This is a very qualitative way of looking at chemical bond. Lewis, of course, himself did a lot of work. This was only one of his work, but one of the great puzzles is that he did not get a Nobel Prize. Many of Lewis's students have got Nobel Prize. Many of his collaborators, he himself did not get. In fact, it was suggested that he should have shared the 1934 Nobel Prize in Chemistry with Harold Urey for his contributions to the separation and study of deuterium and its compounds, and that had he lived longer, he most certainly should have shared the 1954 Nobel Prize in Chemistry with Linus Pauling for his contributions to the theory of chemical bond. In fact, what is very interesting is G.N. Lewis, who was the father of chemical bond in some way, left the field after quantum mechanics came. He was not comfortable with quantum mechanics, actually. Linus Pauling really took up many of G.N. Lewis's ideas, and he actually looked at the valence bond theory. Many people know the valence bond theory was Linus Pauling and many other people, Hitler, London, and so on. But the fact that the chemistry has chemical bond at its heart, and that's the important thing. Why is a bond formed? Why is a bond broken? And that is the heart of chemistry, really started from G.N. Lewis's work. And we understand today that the bonds form because they lower the energy, between the charged particles that compose atoms. And eventually potential energy of the bonded atom must be less than the potential energy of the separated atoms. So of course, there are several ways of looking at the potential energies and later, of course, in quantum mechanical form. I just wanted to write, I don't want to give a lecture on G.L. Lewis, but I think he is a study by himself. He actually, this is some of his own memorandum when he was drawing the octet structure, the lithium as 1, then beryllium, magnesium as 2, and so on, up to octet, the entire octet, all the 8 points of the cube are occupied by an electron. Then Lewis said they have the inert structure, they are less reactive. Lewis also looked at bonding, like metal to non-metal, non-metal to non-metal, metal to metal, as electron transfer, electron share, electron pull. And many of these early chemistries set the stage for the quantum mechanics. Quantum mechanics, which came later in 1926, I mean, this is of course debatable, but many people agree that the Erwin Schrödinger's paper in 1926 was probably historically the first paper of quantum mechanics. And then immediately the quantum chemistry came. So we solved, of course, the Schrödinger equation, which is the focus of the quantum mechanics. And as you will quickly see, this is something that cannot be solved for large systems. And that is the reason I'm going to talk why quantum computers are required. And then came lots of different approximations at different length scale, which are classical, which are not even quantum, like molecular mechanics at the atomistic level. Coarse graining, where groups of atoms interact with another group of atoms. You start to look at molecular dynamics in a classical manner by Newton's law. People also looked at theories in a very empirical manner, a statistical manner, like quantitative structure-activity relationship. This is very widely used today in clinical and medicinal chemistry. Much of these are approximations. Even within quantum mechanics, there are approximations. Why do we need to approximate? We need to approximate simply because we don't have computers. We don't have big computers. We don't have computers which can do this job. And that is where the need for the quantum computers will come in. I must also mention that when I say computational chemistry, of course, this could be replaced by physics or biology, that this is an arm of a triangle which gives the solution to the problem. What we require is not computation, not theory, not experiment, but a solution. A solution which will come from an amalgamation, from a combination of these 3 arms. So computation is going to play a very important role, just as development of theory. Development of approximations will play a very important role because they will always cut down the need for computing time, either the computing time, or they will make the results more and more reliable, more and more accurate. So I think while good theories are required, they will also do a phenomenological understanding. You require computation, you require experiment. The point is, there are a lot of confusions between what is theory and what is computation. It's very hard to define, but I will try to define. A theoretical chemistry or physics, you can replace that by chemistry or physics or biology, may be defined as a mathematical description involved in chemistry, description of physics. Of course, there the physics plays a very important role. Whereas computational chemistry is usually used when a mathematical method is sufficiently developed that it can be automated for implementation on a computer. In theoretical chemistry, chemists, physicists, mathematicians develop algorithms and computer programs to predict atomic and molecular properties and reaction paths for chemical reaction, whereas computational chemistry may simply apply the existing programs to specific chemical questions. So that is as good a definition that one can give between the theoretical and computational chemistry. It's very hard to define many times. Let me tell you, the modern theoretical chemistry, which started after G.L. Lewis. I talked of G.L. Lewis. It started with the molecules. And the first paper of chemical bond was actually done by Walter Heitler and Fritz London in 1927. In fact, 1 year after Schrödinger published his famous paper. This war of hydrogen molecule, H2 molecule, being formed is actually well known as a valence bond theory. That they start with the atomic orbitals and then the product of the atomic orbitals, the covalency or ionicity, describes the valence bond theory. It's very nice. And of course, later on, chemistry changed because we moved from valence bond to molecular orbital theory. So that is a completely different matter. I want to say again, for a theoretical chemist, it is very important that we are developing a mathematical, a logical explanation or a model which connects laboratory observations to the behavior of the underlying atoms, molecules, and materials. So that's how we try to predict the observations, which can, and also observations and which are capable of being tested through experiment. So connection of laboratory observations to molecular behavior is a very important job that the theoretical chemists do. But in the process, what I want to tell today, we can now predict future observations. That is the most important part that has come up, which can later be tested. So the prediction, de novo prediction, novel prediction, is a very important part of computational chemistry. I would not go into the details of this, but I just want to say that many times the connection to the laboratory data by theory is done to properties which cannot be measured, like bond length, bond angle, directly. They are all unreal. They are basically constructs of theories used to relate laboratory measurements, like the spectroscopy data. So I think it's very important to know where the theory plays a role. So example is bond distances. They're actually fitted to spectral data. That's a laboratory data. Vibrational spacing is fitted to obtain dissociation energy, activation energy, properties of reacting molecule at the transition state through transition state theory. Charge of an atom and molecule is completely fictitious, arbitrary. So you require some hypothetical theory, which are probably ad hoc to give you charge of an atom and molecule. So many of these are examples where laboratory data are not directly what we see, what we want, but laboratory data is used by theory to find some of these quantities. Since I'm going to talk about quantum computers and quantum chemistry, I must say what was theoretical chemistry before computers. Very quick history. I already talked of Heitler in London, arguably the first paper in quantum chemistry, in Zeitschrift for Physics. This is basically how atoms form molecules. Very famous paper of Born and Oppenheimer in 1927, we said Born-Oppenheimer's molecule. So that's an approximation that is used today in molecule, the electronic structure theory. Huckel did very nice work. Huckel's early numbers, lots of approximation by Huckel. Many people who know that for large systems at that time, in 1930s, it was impossible to do accurate quantum chemistry. So Huckel simplified many of the problems. Then came the molecular orbital theory by Robert Mulliken. And very interesting electronic structure of molecules, electron affinity, molecular orbital, dipole moment. Many of these were started to be predicted by using quantum chemistry in 1935. Valence bond, I already talked of this, Pauling and Slater's war with Mulliken. So this was a very important war because Mulliken started molecular orbital theory. Pauling and Slater were doing valence bond theory. So they had a very interesting debate. I think those who are interested can read John C. Slater's very famous work on directed valence in polyatomic molecules. What is hybridization? Many of organic chemists, inorganic chemists talk of hybridization. Very interesting paper. Is it yet another kind of orbitals? Coulson and Buffett, 1935 Philosophical Magazine. Max Born at that time started working on theory of liquids in 1920, much earlier. Eyring's transition state theory, I talked about it. I think it's very, very interesting. And Linus Pauling, the nature of chemical bond. Of course, many of you know he's the father of one of the fathers of modern chemistry. And many books which are published by Pauling are very worth reading. I put 1940 as a limiter, that after 1940, what happened was after computers. Because that is where the computers began to come up in any form. Calculators and some small-time computers. One of the major molecular simulation work that took place in a computer, the first one was actually done by Metropolis. And many of you know Metropolis Algorithm, Metropolis, Rosenbluth, etc. In Journal of Chemical Physics in 1953. C.C.J. Ruthan, I must talk about C.C.J. Ruthan. In fact, I should say that I think the resonance, an Indian journal is coming up with an issue where there is a special issue on the CCJ Ruthan. In fact, I'm also supposed to give an article on the CCJ Ruthan. Ruthan's 1951 Review of Modern Physics actually changed the perspective of molecular orbital theory. When it first started to say that the one electron orbitals should not be calculated by solving a radial equation, rather by expansion of the orbitals in terms of a basis, you actually construct a matrix equation, and that made computationally very simple. Although the basis itself has become an issue after that. So very famous CCJ Ruthan, Hall, many of their work. Then the pi electron approximation by M.J.S. Dewar and Longwood Higgins, one of the great scientists, I must tell you, Longwood Higgins. He should have got the boron Nobel Prize with the three-centered boron chemistry along with Lipscomb, I always believe. Proceedings of Physical Society, 1954. Many of these started coming. Carr and Parinello. Of course, many of you know Carr Parinello, very famous Carr Parinello work in Physical Review Letters in 1985. Unified approach for molecular dynamics and density functional theory. Worth reading. Karplus, Martin Karplus work in Nature, Dynamics of Folded Protein. And all of you know Karplus later got the Nobel Prize. Chandler's transition theory. And of course, all this while, I must say, in electronic structure, the couple cluster theory. I have worked on the couple cluster theory. I don't want to emphasize much. But this, meanwhile, became the gold standard of quantum chemistry. I think it's very, very important to realize. Although approximations were always appreciated, Hoffman and Woodward, the conservation of orbital symmetry, Woodward rules, Pouillet's gradients, Foucault's intrinsic reaction coordinate, many of these actually became very, very important. And then came the multiscale simulation, where so far that I have been talking was all of quantum mechanics. Purcell's work, Purcell and Leavitt, and they got Nobel Prize, as you know, with Karplus, in Journal of Molecular Biology in 1976 on what is called the QMMM, where this same one system, a part of a system which is very active is described by quantum mechanics. The part which is not very active, where I can do approximation, is described by classical mechanics, by atomistic, what is called molecular mechanics. This was a turning point, and this started what I would now call multiscale simulation. But entire molecular mechanics, force fields, can be derived for quantum mechanics. And that is the reason I have titled quantum mechanics as a foundation for the multiscale simulation. And from the atomistic simulation, you can again derive the coarse graining. So I think it just goes on from the small to the larger length scale, and I will talk about it. But quantum mechanics was the beginning. It was really a bottom-up approach. And that is where I must say the PM Dirac's very famous statement, which I stated in my introduction, the underlying physical laws necessary for a mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to an equation much too complicated to be soluble. And I think that's a very important statement by PM Dirac. And that is where we believe quantum computers can play a very important role. Today, if you look at chemistry by itself, you think, what is not chemistry? In fact, a lot of people starting from physics, biology, they're all beginning to learn chemistry. From microscopic world to nanotechnology to daily life to environment, life science, human disease, drug design, everything is chemistry. So chemistry in a way is a central science. Only our mind limits its boundary. What cannot computational chemistry deal with? In fact, what is very interesting, whatever I talked here today, computational chemistry can deal with, because we have theories which are beginning to get better and better, from small molecules, DNA, proteins, 3D crystals, surfaces, and so on, structure, properties, spectroscopy, dynamics, reactivity. In fact, may I say, all experiments done in labs can be done in situ. So in the computer, all experiments which are done in labs can be actually done. So there are something called computer experiments today. But what is the problem? The problem is we are limited by computers. And again, I repeat that today, as Dirac said, we are beginning to have fast theories, but we are limited by computers. And I'm repeating this point simply because that's the theme of the workshop. The quantum information, which will lead not only to the general quantum technology, But as a quantum chemist, I say I'd be very interested in quantum computers if it can really put those things. So of course, the theme of computational chemistry as well as computational biology is very similar to have sequencing to evaluation, here structure dynamics and function or reactivity. So that is the theme of the computational science, to understand the structure of a system, dynamics, and look at the functions. And that's what the biologists would like to do. So from atoms, molecules, to big system, nanomaterials, soft matter, and so on, it goes on. And everywhere the computational tools will be used. But unfortunately, because of the complexity of the problem, as Dirac said, we can't use quantum mechanics. So we have to use different methods. So that is the reason I come back to this slide, that we have to use molecular mechanics, we have to use coarse graining, or even sometimes empirical. So for example, if I'm doing protein, I have to use atomistic simulation. If you do membrane, people would probably do coarse graining, mesoscale simulation, not even atomistic. Can I do a membrane by couple cluster, which is a top quantum mechanics methods, quantum chemistry methods? Can I use couple cluster from membrane? Impossible today. Can quantum computer enable it? Answer is yes. Maybe. Depends on how quantum computers move. So that's the fond hope that we have about quantum computers. So I don't want to tell lots of properties which can be calculated today by quantum chemistry, lots of application, reaction pathways, energetics, intermediate, transition state. Many of these can be done today by quantum chemistry. And I think quantum chemistry, quantum mechanics, quantum biology, whatever you tell it doesn't matter. So I think that is where we are. Let me tell you the problems. How big systems can we deal with? Assuming today, I'm just giving an example, I would say typically modest computing setup, what I've written now, number of CPUs, memory, disk space, etc. An ab initio method, which is a quantum chemical method, which actually solves the Schrodinger equation. H psi equal to IS cross del psi del t, and in time independent form, H psi equal to E psi Schrodinger equation. We can, with a very good method like, if not couple cluster, slightly less than couple cluster, we can certainly do 100 atoms. 100 atoms, these are actually ab initio methods. I call it methods which calculate the wave function. They scale, and this is the problem, they scale already n to the 4 to n to the 7, at least. The couple clusters, singles, doubles, triples, which I'm going to come, which is a very, very good method, scales as n to the 7. Now, one can imagine what is n to the 7. So if I go from 100 to 200 atoms, my computing time will go by 2 to the power 7, which is an enormous problem. So you can easily see how things can blow up. If we use a slightly watered down method of ab initio, many people actually call it ab initio as well, but I want to separate it because it does not calculate the wave function. It is called the density functional theory. This can actually have 1,000 atoms in the same setup. It goes n to the 4. Semi-empirical methods, which are nearly obsolete today, where you use the Hamiltonian, but do not solve it exactly by first principle, not exactly by first principle. You use some empirical methods to simplify. You can go one step more, 10,000 atoms, one order of magnitude more, because this scales NQ. So a very typical problem that we're discussing. And then you can have a molecular mechanics. I told you atomistic simulation. You can go to 100,000 atoms because this scales n squared. So I think a very typical situation is that today, if you have a large system, you'll be tempted to use n squared. So depending on your problem, you choose method. Within ab initio methods, also there are variations. So this is what I call horses for the courses, sorry. So depending on depending on a horse course, you put your horse. So it's very important to realize the horses for the courses approach that we use in quantum chemistry, in computational chemistry today, or computational biology today. Couple cluster, on the other hand, is a method which can get all of these, including proteins and so on, very, very accurately. And that is the reason I'm calling it gold standard. It is not exact. You can have an exact coupled cluster, but that's no good. But an approximate coupled cluster with singles, doubles, and triples has already become gold standard, which means you get results within chemical accuracy. And that's very, very important, to get results within chemical accuracy. 1 kilocalorie per mole at least. The problem, as I stated, is n⁻⁷ scaling. So although it's very, very accurate, you cannot do very large systems. Computer will just not allow, or it will just go on endlessly. Some of the problems will never end. It is very accurate, as I said, with the chemical accuracy. In fact, with the multi-reference versions, you can do excited states, electron attach, ionization, potential surface. So a lot of interesting chemistry we can do at high accuracy. However, computational limitations do not allow us to use coupled cluster for many cases, and hence we use methods like DFT, semi-empirical, molecular mechanics. I have to understand that. If I had large enough computers, I would simply say, don't do anything. Do either coupled cluster or multi-reference versions of coupled cluster and develop theories. Now, it's very nice to say for me, because I work on coupled cluster, I would say, don't do anything. But the point is, today we can't do, because we don't have computers. So that is the reason we have to develop approximations. We have to develop different approximations which work for different systems. Let me tell you, within the ab initio, DFT, and semi-empirical, it's a very qualitative curve. So I have given number of atoms 1. 1 doesn't mean 1. It can be 10, 100, whatever, 1 unit. You get an accuracy in the full CI. So accuracy is very large. And these are the error bar. And as you can see, as you go to semi-empirical method, the error bar actually increases. These are 10 kilocalorie per mole. This is point. So this is accuracy of the order of 0.1 kilocalorie per mole. So as you are going down, actually it is becoming worse in the y-axis. So you can see coupled cluster or multi-reference coupled cluster is very, very good. But the problem is the number of units that you can do is very small. Then it's very hard to say what are the next methods. I don't want to go into the methods, but non-local density functional theory or the perturbation theory is next. Local density functional theory is cheaper. So the accuracy is less, but again, more number of units, and eventually semi-empirical method. It's a very qualitative curve, just to tell you where the methods are stacked. So more accurate the methods are, the less number of atoms or molecules it can handle, the size it can handle. That is the whole problem, size versus accuracy, because of the n dependence, large n dependence. Of course, very interestingly, chemists want to do equilibrium bond length. That's the very first thing. But there are so many calculations that one has to do to get the equilibrium bond length. Then calculate the 0-point vibrational energy, add that. So I think there are lots of things that one can do. So the point that I'm trying to say, this is a very important curve for the multiscale simulation, that I'm eventually forced to bring approximations. At the angstrom, and this is the length scale, at the angstrom, I have ab initio methods. So electronic structure, which is molecular orbital, DFT, that's all, coupled cluster, everything comes here, even quantum Monte Carlo, and so on. If you go to the next length scale, you have what is called atomistic length simulation. This is where the proteins, for example, many people are working on protein, they can't use this simply because it is just not possible. But if you ideally ask, this should work everywhere, because this is exact. The quantum mechanics is exact as you can solve it. But we don't even use quantum mechanics simply because it is not possible. You go to further polymers, membranes, you use mesoscale simulation. That's what I mean by coarse graining. And the other spectrum is the engineering length scale, which are independently developed. What is interesting today is to look at these two length scales from the quantum mechanics. Top things from the bottom. So bottom-up approach. From here, can we go up? And that's what people are doing. Engineering length scales, of course, got developed much earlier. The engineering, fluid dynamics, Brownian dynamics, lattice Boltzmann, they came up much earlier. Of course, it would be interesting theoretically to connect from here to here as well. Can we now explain the engineering theories, classical theories from here? And I think that has been a great way to look at the theory of multiscale simulations. That can I look at a less accurate theory? Can I develop its approximations from a more accurate theory at a small length scale? So that has been the focus of the simulation method. Today, of course, with this, you can even do nanomaterials. And I talk of nanomaterials because it's very important length scale. So many people are using atomistic simulation. I put it here, somewhere here, nanomaterial. But can we use quantum mechanics? In fact, nanomaterials itself has come up wonderfully well. 1952, Schrödinger, very famous statement of Erwin Schrödinger, we would never experiment with one electron, atom, or molecule. One electron. But 1960, Richard Feynman told us there are no physical limitations to arranging the atoms the way you want. And that is very, very important. There is plenty of room at the bottom. Within 8 years, you can see how the vibes changed. By 1980s, the nanomaterials, nanoscience actually came into existence. The major discovery that started was basically the scanning tunneling microscopy. And that radically changed the ways because we started looking at these atoms and molecules, single atoms and molecules. The nano world really started. Another significant development which came from IBM Zurich lab, which actually received a Nobel Prize in Physics in 1996 by Binning, Quattey, and Gerber. They invented the microscopy of SEM along with the atomic force microscope. So I talked of scanning, but also AFN, so the same year. So this was a very, very significant development. Along with, I would say, the fullerenes in 1990s, fullerenes, the Buckminster fullerene. I think these are very, very important developments in nanoscience. But today what I want to tell, the theoreticians are able to describe nanoscience in some approximations, with atomistic length scale, probably even a model by density functional theory at least. So that has been a very great work that people have been doing. And certainly all of this can be improved if we have quantum computers. So I would just talk a little bit about quantum computers, how that will change. Of course, we know that what is quantum information. Let me first say, it's a physical information that is held in the state of a quantum system. So let's say if I take a two-state quantum system, basically there'll be only 0 and 1. In the quantum, I can have a combination of the two states between 0 and 1, like atomic levels n plus 1. There are two spin states, there could be polarization, so several ways. So this is what they call quantum qubit. So the combination allows a lot more possibilities, unlike just the two pure states. And I think that is where the quantum information can help. You can have more qubits. So you have A and B, so you have 0 on both A and B, 0 on 1, 1 on 1, and so on. So these are the classical qubits, and then you can have a linear combination of the four states that will then become quantum. I can have n qubits, and I will have many, many linear combinations, just like quantum chemists do, actually, a linear combination of configurations. So it's much like it's a superposition theory that the linear combination of the states encompasses the possibility of the power of the quantum, the information. So this is what is basically called the quantum entanglement. So this is helping in passing of information from A to B. The entanglement is extremely important. I'm sure there'll be a lot of good lectures on how this will happen. I'm not an expert, but I thought I will just mention in a few slides that how quantum information, by using simple quantum mechanics, which all of us are using as a sum over states kind of problem, which is basically superposition of states, can help in developing the quantum computer. So quantum computer will actually use this quantum mechanical phenomena of superposition and entanglement to perform operations on data. Quantum computers will solve problems which much faster than the classical computers. It can simulate much faster than the classical computers, any simulation problems. One of the important advantages is that they are reversible and can save energy. And I'm sure a lot of experts will talk of quantum technology, so I'm just giving a very brief overview how quantum computers will help. Some example, and this is something that I have taken from the web. So I mean, the experts will be able to tell if I'm wrong. Given an integer, a problem is, let's say, find its prime factors. In a classical computer, the time that it will take will be 2 to the power order of ln n to the power 1/3. Natural logarithm n to the power 1/3. In a quantum computer, it will simply be order of ln n squared. There is no 2 to the power. So you can imagine, as you go for large n, how much quickly one can do it. This is the CPU time. And just giving one example, how things will be simplified. We have an unsorted database search. So find a given element in a database of size n. In a classical thing, it will be order n. In a quantum computer, this will become order n to the half. Feynman's very famous statement on simulation. Classical computers require exponential time to simulate many particle problems. Quantum computers will require polynomial time, and that is very, very important. It's not that it is simple, but it is at polynomial time. So this is Feynman's famous quote that so how simulation problems can be simplified by using quantum computers. And I think this is where the current state, unfortunately, the present status is that we can control and couple the individual qubits. That is good. The number of qubits are very important. So how do you, I want to tell again, how do you enlarge the power by having more and more qubits? I took an example of 4 qubits, A and B. Okay, but you can have n qubits, and then your linear combination will be many more. So the problem is to have, and this is the technology, the problem is to have more and more qubits. Again, the experts will tell what is the present state, but as far as I understand, the current running algorithm works well with about 10 qubits, which is good, but I think we may require 10,000, 100,000 qubits, best computers. That's the state of the art, probably, which we require. Once that comes, I think we can solve many problems very, very accurately. And that is a punchline that I'm going to tell. Many problems for which today we are using watered down theories which are very simple, can be solved by quantum computers. And I think that is the technology that we'd like to hear. What is the present state? Again, as I said, I'm not an expert on the present state, but certainly we would like to know. In the final part, which will be last 10 minutes, that's my time will come up. I will just talk about a little bit about the kind of problems that I am doing. I already talked to you about what can quantum chemistry do. I thought it would be unfair if I don't tell you what we are doing. So we are, of course, working on several highly correlated theories, and in particular, of course, the coupled cluster that I talked up, to develop electronic structure. And a very interesting problem that we are doing is a physics problem of resonance, which is not a bound state problem, but using bound state methods to the resonance and decay problems by using what I would call complex absorbing potential. I will come to that a little bit later. So we are basically, our main focus has been to develop many-body coupled cluster methods for molecular properties. I also did a little bit of work on density functional theory and qualitative quantum mechanics to address the local reactivity of molecules. And then lots of interesting application to materials, functional materials, hydrogen storage, and so on. I will again come a little bit about that, computational catalysis, and so on. These are some of the work that we are doing. Many-body coupled cluster theory for molecular properties. In fact, we started from my days of PhD to develop coupled cluster method. These are really theoretical work and with a very little, I would say, semi-empirical level calculations. In 1982, 84, all this started in Kolkata at that time. Then, of course, it moved to NCL. So this was one of my first leading papers from National Chemical Laboratory, Pune, the 1984 paper, and continued here. Then lots of physical review papers, chemical physics letters, and so on. I went abroad and also worked on coupled cluster. And a very important coupled cluster that we developed for molecular properties was the extended coupled cluster based on a functional by Jouko Arponen in 1983. In fact, some of us, with my collaborators, we developed in Pune which was truncating and fully size extensive. So many of these have an advantage over the average value, expectation value coupled cluster. And all of these had a 2n+1 rule. So it was easy to develop for derivatives of energy. Then early days, as I started in 1980s, late 80s, the multi-reference coupled cluster theory was being developed. And we, for the first time, developed in the world molecular response properties to the multi-reference coupled cluster in 2004. It was only, again, a formalism at that time. And then much later, we started to do the coding. We looked at application to electric and magnetic properties, and we compared the related equation of motion coupled cluster approaches. We also developed low scaling many-body coupled cluster approximation, which is very important to do, because coupled cluster, as I said, singles, doubles, triples are n to the 7, but singles and doubles are n to the 6. We also did some scaling down from n to the 6 to n to the 5 with some approximation. So that also has to go on. So while I'm pitching for highly accurate computer, let me say that the quest for good theory, low scale theory should continue, because these two together is going to advance the physics. So an interesting application. So what we did later was a resonance and decay problem, and that's what I want to tell you. We did in the middle of 2000, the first decade of 21st century, we started looking at resonance problem using coupled cluster. So many people say, okay, this is not possible because coupled cluster is for bound state and the wave function has to be square integrable. Whereas resonance states and decay states are those states for which wave functions are non-square integrable. But we put complex absorbing potential, and one can show that with that, if you have a real part of an electron affinity, which is complex now because you have a complex potential, the real part is the resonance energy, the imaginary part is the decay. And we could actually look at shape resonance, Auger decay, interatomic Coulombic decay. This is a very fascinating experiment, actually, interatomic Coulombic decay. Even resonance of excited state. Very recently, in this paper in molecular physics, we actually looked at SO2, excited state resonance. So there are very interesting things that one could actually do, and many of which I have written down in a review, in a feature article last year in the Journal of Physical Chemistry on this particular subject. Another recent work that I'm doing is more of physics, where we are now developing relativistic coupled cluster to take into account the subtle spin orbit coupling and relativistic effects. So within the coupled cluster, many of the coupled clusters that we developed were non-relativistic. We started to put in relativistic theories. We did ionization, electron affinity, double ionization, PT-odd interaction, electric and magnetic properties. We identified mercury hydride with a high dipole moment, radium fluoride as a candidate for parity time violating interactions, and so on. So as you can see, each of them really deserves a separate lecture. But what I want to tell you that many of these calculations were done with such high accuracy that we could be confident of many of the results. So this is what I have actually given here. This part is the highly correlated electronic structure methods, and we paraphrase this. And this is where I want to emphasize right results for the right reasons. So I want to emphasize it is not enough to get right results, but you must get right results for the right reasons. And that is what the coupled cluster allows you. So I'm pitching for coupled cluster simply because of this. Unfortunately, we cannot do because of the lack of high-powered computers, despite all the progress in the method that we are doing. So I told you here, let's have coupled cluster relativistic theories. In fact, more recently, we have also added electron-nuclear scalar pseudo-interaction. Lots of recent papers, including papers in last years. And then this bound state coupled cluster method for resonance and decay. So these two are very new work, which has started in last 7 or 8 years. Some of them started even 15 years back, but more actively 7, 8 years that we have been doing, apart from the early coupled cluster for ionization response properties that I talked about. However, when I looked at material science, they are still too big to be handled by coupled cluster. And that is where, as Nilanjana said, that I looked at computational material science And in particular, I'm going to talk a few results on gold clusters, aluminum clusters, and in general, catalysis, hydrogen storage material. They are very, very important for renewable energy. Environmental problem of N2O reduction by carbon monoxide. Much of these had to be done with DFT, with density functional theory, which is also pretty good because it actually takes care of exchange and the correlations, though not in a very predictable way, but it is certainly quite good. So the density functional theory has been used for much of this work. A very few interesting results. Hydrogen chemisol gold and silver cluster for oxygen activation and CO oxidation, oxidative addition of carbon iodine bond, and aluminum nanoclusters. Endoheterally doped gold cases for efficient activation, O2 activation, and CO oxidation. So you can see that we have been trying to put many of these clusters doping. For example, for this one, if you do native gold and silver cluster, it is not that good. If the moment you put hydrogen atom chemisorption, it really improves. The activity improves. So here also endoheterally doped gold nanocage. Radical attached aluminum cluster. Aluminum clusters on boron nitride doped graphene support. This is a very, very exciting catalyst that I am looking at to do a nitrogen activation. As all of you know, dinitrogen activation is a very important problem. It is not graphene. On a graphene, you put boron nitride and then put aluminum clusters, or small aluminum clusters. So we found that that can activate dinitrogen. I think it's very important that many of these are theoretical predictions which are yet to be experimentally realized. In a collaborative work with a group in Pune of Professor Vidya Osare, we have been working on catalyst designing, where we look at ligand selection, coordination of sites, solvent selection. So catalysis designing is one problem where not only you have so many things to do, you can actually use artificial intelligence, machine learning, but this is where quantum computing can help. So many of the people who are actually developing quantum computers, I really request that we can even collaborate. So we can take our problems and make a test case that how good is the computer, how quickly it can now solve. So designing de novo design of catalysis is one important problem. So for example, here, when I talked of aluminum clusters on boron nitride, somehow we had an intuition. The intuition worked. But if you have a completely de novo design, it's not very easy. So I think this is very, very important, and it requires a large amount of collaboration with a lot of people. People who are also working on artificial intelligence, machine learning, or various computational tools. So one of the important problems that we have, and this is a government imprint project that we have with my collaborators at IIT Bombay and in Pune, on homogeneous catalyst for carbon dioxide activation. So I have a carbon dioxide activation, want to put carbon dioxide to formate and eventually to formic acid. So it's a very important problem because that way we can remove CO2 from the atmosphere. But again, it requires, we are looking at homogeneous catalysis. Some of my collaborators are also looking at heterogeneous catalysis, but I think it's a very, very important problem where again, collaboration can do. A lot of people are doing CO2 activation, but it's not very easy to have something in the market. So eventually we are also having an industry partner who can translate it. So we are really looking at from bench scale to market. And that is very important today. Very quickly, I will talk of some of these clusters that I talked of, gold and silver catalysis for oxidation reaction. They're exciting. So one of the important things to see how the clusters behave. If you have gold 8, it is inert. But if you just put one gold replaced by silicon, it becomes catalytically active. If you have pristine gold, it's not so good. But if you put metal inside the cage, and I talked about this, it gets activated. I talked about this also, hydrogen atom chemisol, aluminum cluster on boron nitride doped graphene. Very, very interesting work. So some of the problems I will show how time consuming they are. So this is, for example, the AU18 gold cluster, pristine, CO oxidation. This is a computational mechanism. You have a transition state, intermediate. These are extremely complicated reactions because you have so many reaction coordinates, I must tell you. To find out the transition states are very important because then you know whether it works at room temperature or not. So this is the barrier. You can see that we have two barriers, 0.71 and 0.45 on the AU18. It goes to CO2. Look at the same curve, which is doped. So now what I've done is AU18 was sodium inside, AU18 with potassium inside, magnesium inside, calcium inside. Look at the activation barriers. The same reaction, the barriers have all dropped down. If you compare with this barrier, they have all dropped down. 0.71, 0.45, they have all dropped down. Of course, many people will argue sodium is extremely difficult to synthesize. But I believe magnesium will be easy to synthesize. Magnesium at go AU18. And this is still better. Or even calcium. Potassium is also very good. So what I'm trying to say, theoretically, we can predict what kind of catalyst will actually do. So again, same thing. I look at hydrogen chemisorption. You look at AU6 and AU8. I do the same reaction. There is no O2 activation. Same CO going to CO2. Barrier is very, very high. Just look at this. I just put one hydrogen atom. AU6H, AU8H. How brilliantly the barrier comes down. From 0.7 to 1, 0.002, almost barrierless, 1.193 to 0.360. The binding energy increases, the oxygen gets elongated. So I have a beautiful example of very small tweaking, but de novo design is still much more difficult because we have some hint. And it's very hard for me to tell you, how did I come up with this catalyst? So there are some hints, I should tell you that. And that is very, very important. We have also applied DFT. I will not talk much about it for lithium-ion batteries. In fact, very recently, we have been working on lithium-ion batteries with the molybdenum sulfide. With this semiconductors of 2,6 kind of semiconductors. And we found that they are very good with high stability, large surface areas, and so on. So I think these are also very recent work that we have done. Again, the defects of lithium sodium adsorption and molybdenum sulfide, LiBs kind of material. So we are saying that these materials can be much better battery materials. So they have again been published in Journal of Physical Chemistry. Those who are interested can look at it. I want to, because I have not to, my time is up. So I would like to end by saying that a very important problem that I'm doing, I wrote down there is the onboard hydrogen storage material. Unfortunately, I could not show. We are also looking at MOF, COF, ZIF, which are basically porous material, doping them to give very good hydrogen storage properties. The results are, some of the results are exciting, but they're still not to an extent that it can be translated to the market. For example, we have got a result of scandium in MOF5, scandium in ZIF7. They are very good results. Scandium does a very good thing, doping of scandium, I can just tell you. And it is not a heavy metal, it's a light metal, so the entire catalyst does not become very heavy. So your gravimetric storage is very good. I didn't talk about it, so I just thought I would tell you in words. I want to now end with an outlook that the fundamental insight is very, very important, from atomic and molecular level to nano and bulk. So different length scales, we have combined different theoretical methods. How to combine, what to combine will certainly change as the computers change, as the quantum computers come. And I think this interconnection will provide a very good insight. What is the path forward? Of course, we need accurate methods for large systems. And this is the emphasis that I'm giving. We are using algorithms, strategies. One of the strategies is fragmentation. We fragment the system into subunits which are weakly interacting. That is one strategy. But of course, if you have computers, it will always help. Then the second strategy is to develop approximations which are not so accurate, but which are reasonable, appropriate multiscale simulations. That is what I said. Problems of strong correlation require very accurate methods. So some of this cannot be done even by appropriate multiscale simulation. I also talked about grafting artificial intelligence and machine learning, even if you have a very good computer. These are tools which will help, because you don't want to use computer unintelligently. So you would like to have artificial intelligence and machine learning. I talked about catalyst design, but many other problems, pharmaceutical problems, de novo pharma design or drug, you can use it. I'm looking at material genomics, the path forward. Can you have a database of genomics, just like molecular genomics? Material genomics, so lots of material database will be there, and maybe a QSAR kind of extrapolation can be done with material genomics. I want to close with lots of challenges in terms of computation. I don't know whether this slide is too small, but let me read density functional theory. To improve density functional theory, improvement of prediction of band structure, optical properties, complex system, strongly correlated systems. I spoke much less about it, but this is a very, very difficult problem. Because here, approximate methods will fail. So you require really accurate methods. Similarly, for large systems, non-adiabatic molecular dynamics, we cannot do today. So we require very powerful computer. Cluster expansion to large systems, you can't do today. The challenges I'm again repeating. Identification of molecules for drug design, new functional materials in renewable energy sector, storage, conversion of CO2, and of course, artificial intelligence and machine learning in coding and functional use. So there are some of these, I just wanted to end with this, some of these interesting computational as well as theoretical problems. Many of them are theoretical problems. For example, improvement of exchange correlation function on DFT is continuing. Because DFT is good, but it is still not that accurate. It is still not systematic. So that improvement is also very, very important. So I have put them down in this final slide. What are the things that we need to do? What are the things for which a quantum computer, along with great theory, great algorithm, will help? I think with this, I will end my talk, acknowledge materials that I have collected from different sources. Wherever possible, I have tried to quote, but there are many materials that I have taken from different sources. And of course, funding agencies for my work, and there are a large number of them, starting from SER, IR, DST, Board of Research in Nuclear Science, Indo-European Union, DST DART, many other funding agencies that I have got help from. And of course, a large number of students. Nilanjana spoke about it. I think I graduated more than 40 students. And I still have many more students to get graduated. So more than 40 students, working in theoretical chemistry. Many people actually have, we have problems in getting students also, even sometimes. I have been very lucky that from my beginning, I got good students. I got students who are motivated to do theory. So many of them are now well placed. I must thank all of them. It's very hard to put down all the names, but let me thank all my students and of course my collaborators. I mentioned one of them for catalysis. There are many collaborators who are now doing on the imprint projects and so on, and collaborators all around the world. And I'm very thankful to them all around the world. Thank you very much for your patient listening.
Thank you, Professor Pal, for this excellent exposition, starting from the history down to the challenges and how quantum information theory might possibly help in the advancement of different levels of computational material science. So thank you very much. It was a really nice overview, compacted in a short amount of time. We have about 20 minutes for questions. Now, there are several questions that have been channeled to me from the YouTube, broadcast. But I will ask first the audience present here on Zoom. If you have any questions, please, raise your hand or type it in the chat box. Audience present here.
Should I stop share or?
You may do that.
Let me see here.
So there are plenty of questions from students from the YouTube channel, but are there any questions from the audience here? Okay, let me start with the YouTube questions then. They have been channeled into my chat box. Okay, some of them are actually a little bit basic because I think there are plenty of students out here, and some of them are really because they probably haven't taken any quantum mechanics during their course. So Shruti Swaroop asks, sir, can we use quantum mechanics for every field of science, from biological to material to energetics and also chemical level?
Okay, so I think, that is what I was going to say. We can't use today simply because challenging problems. But if you ask, can we do it, given everything at your disposal, the answer would probably be yes. And that is what Dirac said, that all problems are in principle soluble. Because by using quantum mechanics, the reason I'm saying is the following. You look at a cricket ball, do you need to use quantum mechanics? Of course, no. You can use classical mechanics, right? But what is a cricket ball? It consists of atoms and molecules. Who follow quantum mechanics? So there's a very important question, a philosophical question. Why is it that cricket ball does not follow quantum mechanics? Yet all its constituent particles follow quantum mechanics. The answer that I will give is that does it not follow quantum mechanics? And in fact, I would say, yes, it does follow quantum mechanics, except remember the Bohr's very famous correspondence principle that in the limit h tending to 0, quantum principles become classical. What it means is that the system is so small that h is practically taken to be 0, the universal Planck's constant. So then you don't need quantum mechanics, but doesn't mean that there is no uncertainty, no quantum uncertainty, but these are practically immeasurable compared to the experiment. So in many of the bulk, the experiments are at such a length that you don't need quantum mechanics. So you don't like to complicate your life unnecessarily. So my answer there would be no, you don't need in many problems. But there are many problems where we need, like biology. If I would solve a membrane-drug interaction, I would actually like to solve quantum mechanically, fully. But I cannot do that because I don't have computers. So the answer is yes, many problems I would like to use quantum mechanics, but yes, in certain problems I don't need quantum mechanics simply because it is meaningless, not because quantum mechanics is wrong, but it is simply meaningless to do that. So that would be my answer. But yeah, in principle, yes, most problems do follow quantum mechanics, but everything starts from electrons, atoms, molecules, right?
Thank you, Professor Pal. There's another question from Sriparna Ganguly, and she's asking, is the n to the power 7 scale, is it computationally equivalent to the computational complexity upper bound of the order of n to the power 7 that we use in computer science? So, here n was the number of atoms. So she's trying to understand if that scaling is the same as upper bound of the order of n to the power 7 that is used in computer science.
Yeah, so here, of course, there is no upper bound. Depending on the methods, you can even go to n factorial scaling, depending on the method that you use. So I said n to the 7 for CCSGT triples, but if you use a higher level, even higher level, it's not required because by triples, you all usually get chemical accuracy again, but you can have a larger scale in terms of n to the 8, even n to the 8 is possible. So it's not that is the upper bound of n to the 7. So that is what I want to say. So obviously it's a little bit more expensive, but typically with n to the 7, you are right. That's a typical upper bound that we are happy with. That if you can solve a problem of n to the 7 nature, I think you are okay for most purposes because I get the chemical accuracy.
Okay. Thank you. From Ayush Arya, what would make quantum computers ideal for molecular modeling? What's different in their way of computation or their way of programming that makes them superior to classical ones?
Yes. So as I said, the quantum computers will use qubits, quantum bits. And by the entanglement, they will be able to process many more information. Like if you have just a 2-state, you have only 2 states. And in a very simple way, I'll say, if you take a linear combination of 2 states, by changing the combination coefficients, you can generate many states. Not just 0 and 1, but many combinations of 0 and 1. So by using many qubits, you are actually able to generate many states, so the physical information can be stored much more easily. The passing will be done much better. So obviously, this is a different technology. And I think as far as the technology is concerned, yes, I'm not the expert, but I'm sure in this workshop, people will actually say how these qubits should be put together to build quantum computers. So I'm just telling how it can be done with the qubits, because it's just like an entanglement, entangled states. And there, the information passing becomes very easy because of entanglement. Otherwise, let's say you have A and B, they can remain decoupled. The information passes straight, and no new value addition is done. So this is a difference between the classical thing where there's an isolated state and a quantum superposition where you can through the entanglement you can actually increase the information. So that's what I understand. But of course, if you ask me how will they actually manufacture the computer, I will not be able to tell. The technology will be certainly discussed of the qubit. The algorithms must use them now. So our algorithms also have to change on the qubits, but many of the basic parts will remain the same. Okay, basic mathematical algorithm part will remain the same. How we program will certainly change.
Thank you. So I just would like to ask the audience again, if they have any questions, they can either raise their hand or type it in. While that is being done, there's an interesting question from Bhavesh Chandwani, and he is just plainly asking, if quantum mechanics and quantum computers is the future of science, then why are we still learning the classical methods?
Well, as I said, I told right in the beginning, you do not use quantum mechanics for cricket ball. Because it is like bringing an elephant to kill a mosquito. Exactly. I hope you understand. So if you are going to do that at any point of time, that's not doing science. Because they have a completely different realm. I am now trying to explain classical mechanics from quantum mechanics. That is completely different. That I am saying that for all classical objects, the uncertainty is immeasurable. So although there are electrons, atoms, and molecules, they are governed by uncertainties. That is immeasurable for classical objects. So you can neglect it. This is exactly what was taught in the Bohr's correspondence principle in the limit h tending to 0. Or if you look at lambda equal to h by p, that p is very large, lambda goes to 0. So this tends to 0. This is actually engraved in quantum mechanics. So if you want a very provocative statement from me, yes, I will say classical mechanics is the limit of quantum mechanics. I do not know if everybody will agree with me, but I would say classical mechanics is the limit of quantum mechanics. But having understood that, I will not use quantum mechanics to solve classical problems. Of course not. So that is not the message that I'm giving. The message that I'm giving are there are systems where quantum mechanics is very important. So like biological systems, like nanomaterials, systems which are big enough, but where quantum mechanics is important, we are not able to use them. So the message is not to use quantum mechanics for classical systems where you don't need it. Yet I would say I can explain why we don't need it by my philosophy of quantum mechanics, by philosophy of Bohr's correspondence principle, by the de Broglie's wave particle duality. So those are very important philosophical understanding. But at the end, we don't need for classical systems, but we certainly need for many other systems. Systems of material science, even biology, and of course, all of chemistry that we do. So I think, but even there, we are not able to do the best of the quantum mechanics problem. It is not a question of quantum versus classical. Within quantum, we are not able to use the most accurate methods. Please try to understand, even within quantum. And that is the focus. The focus is not to use quantum mechanics for classical problems. Okay, I'm sorry if that was the message. That has gone, that's not the message.
I think Digyash Kumar Bhattacharya needs a comment from you. He's asking, can computational chemistry help in a great deal for organic synthesis? So I think,
Of course, yes. A lot of the organic synthesis depends on two very important factors. One is thermodynamics how much energy we'll gain and lose, the stability, and of course, how fast the reaction will take place. So all of these can be actually done by computational chemistry. That is, if you have A to B synthesis, by all possible means, you can get the reaction mechanism. Do you require a catalysis? Do you not require a catalysis? And if you do catalysis, if you don't do catalysis, how much will be the gain? And what is the energetics? You can even talk of the stability of that system by doing molecular dynamics. That the system that you get as a product, is it stable? Or is it a millisecond stable, nanosecond stable, second stable? Of course, organic chemists want stability. So that can also be judged by computational chemistry. So yes, the answer is yes. Emphatic yes, according to me.
Yes, thank you. So I think we can take a couple of more questions. So this is a question from Surya Prashant. He's asking, is the polynomial time the time taken to compute a specific function? Example, a Legendre polynomial or a Laguerre polynomial. So some clarification is what is sought there.
Yeah, so of course, yeah, that depends on the problem. When you said polynomial time, it's a general thing. The simulation, that depends on the simulation problem, type of problem. What polynomial? It can be even quadratic, cubic, whatever. It can be kind of polynomials that you're talking about. They're all basically power series polynomial. But the point is that they are less than exponential. That's the point. And hence, the quantum computers will do it faster.
Okay.
So that will be the nature of algorithm when you do with the qubits. Yeah.
Mm-hmm. Mm-hmm. Okay, I don't see any questions from directly from the audience, but there are actually a ton of questions coming from the students. So I'll take one other student question. This is Sushma Hariprasad, who thanks you for an amazing session. And she's asking, what do you think is another main failure for classical? I think she's meaning to say, what is the main failure of classical computer compared to quantum computer other than solving the period difference? I think the question itself is a little, but the gist of it is...
Yeah, so I think,
please.
Yeah, I'll try to answer as much as possible, whatever I understand. Yeah, I mean, the major failure of the classical computer is that, see, you have to also understand the classical computer has come a long way. There is nothing called one classical computer. The classical computer today is also very fast. The processors are getting faster because of the technology, the electronics technology, and so on. So the information passing is becoming faster and faster, even within the classical computer. So to say a classical and a quantum computer and say that this is this and this is really not correct. Within the classical computer also there is a variation in speed from early days to today. You all know that the computers have become faster and faster, right? The point that we are trying to tell here is that the quantum computer, why am I distinguishing? Because it uses a completely different technology. It uses quantum mechanics, quantum entanglement to build a computer. The fact that it speeds up further is the reward that we get. But first of all, the difference of quantum computer and classical computer is the technology difference, not just the speed difference. The speed difference is the reward that the speed that the quantum computers can reach will probably not be reached by any development in classical computing. Now, again, this is a futuristic statement. I will not, it's a kind of predictive statement. I can't tell that. A classical computer may or may not, but I think it will never reach because quantum computers are always having a technology of entanglement, which is better. So that is all I can say. But it's not to say that the classical computers are not fast. I mean, that is a very loose way of talking of it. I would say the technology, first of all, is different because you are using quantum mechanics to build a quantum computer. That is not used in classical computing. And the fact that this helps in speeding up in a significant way is certainly the reward for which the quantum information and quantum technology have become so popular in the world.
So there are plenty of questions, but I'll take one last question, which I think is an excellent one. Aman Jamwal is asking, can quantum computing enhance spectroscopic techniques to identify compounds? I think that is a very innovative question. Can we use quantum computing?
Yes. In principle, probably yes, because today even spectroscopic techniques are subjected to computer evaluation, right? They actually push it through the computer, and then quick throughput comes up. So I would say in principle, yes. And of course, spectroscopy data, whatever spectroscopy data provides, they can be computed independently, be it in gas phase, be it in solution phase. So independently in silico, I can do it faster. But if you are saying those instruments which are connected to computer, even there I would say there would be a speed up if you use quantum computers. So there will be quick throughput analysis. So in that sense, spectroscopy experiment can also benefit. I think there are two ways of answering this. That one is de novo prediction of spectroscopic data in silico. That will be also done. And spectroscopic experiments which are connected to computer, they can also get benefited. So I do not know which is your question. So I answered both. Both are possible.
Yeah. Thank you. So there are plenty of questions, but I will suggest that, please write your questions to the coordinator of the school, and I can work with the coordinator, filter a few more questions, and perhaps write to Professor Pal. And I'm sure, though he's an extremely busy person, he might briefly find time to answer a select number of these other questions as well, because I know that he's also an excellent teacher who loves to spend time with students. So I'm sure you'll be able to find time to answer a few of them.
Yeah, I will do that. I'm very happy that there are so many questions, first of all.
Yes.
It's very good to have so many questions. And as I will tell, the very famous teacher said this, there is nothing called a stupid question.
Absolutely.
So do not worry about the level of your question. There is nothing called a stupid question. And I always say, you are nothing if you are not even a stupid.
Thank you.
I hope you understand, yeah. So please ask questions, no problem. And please feel free to ask questions. I think it's very, very important. And I would definitely try to answer, yes.
I would request the coordinator to actually summarize the other questions that were not taken in and pass it to me. I will have a look at them, and I will please take a subset of them and channel it to Professor Pal.
Yeah.
Thank you.
So
Professor
if there are some questions, yeah.
Yes, please go ahead.
I just want to tell Professor Panigrahi, if there are some special question answer sessions after tutorial, something, then I can come back. That time I also can answer some of these questions. Or I can write them by email, whatever. Okay. So, yeah.
So
okay.
Thank you so much, Professor Pal. It was an excellent session, and I enjoyed chairing it. And I'm sure, it's clear that you enjoyed giving this talk on such an upcoming.
Thank you for chairing, first of all.
Thank
you for chairing. Yeah.
Yeah, this thing, gels in seamlessly with your own research interests. So it's kind of, beautiful, continuation of, of your own interests as well and mine as well. So I think this was wonderful. And I want to thank the organizers.
Thank you.
I would also like to thank the organizers for inviting me to chair this session. I enjoyed it thoroughly. And I would like to hand it back to the organizers now. There's a second session where Professor Howard Weisman from Griffith University will present us. Thank you very much.
Thank you all. Thank you all. Thank you, organizers. Thank you all. Thank you, Professor Panigrahi. Thank you, Nilanjana, for sharing.
Thank you.
Thank you, Nilanjana. Thank you, Professor Pal. Thank you, organizers. Yeah. Thank you. Yes, yeah. Thank you, Nilanjana.
Thank you.
Thank you. Thank you.
Hi, Professor Weisman. Hello.
Hi, how are you?
I'm well. Yes.
Okay.
So who's, we're not live, right? No.
Yeah. Professor Panigrahi?
I can tell.
Professor Panigrahi?
Yeah, I was momentarily having problem. You can start, Alok.
Should we start or we take a 1 minute break? It's okay?
Yeah. Okay. And the questions will be fed to you by our coordinators.
Maybe I can take a look at the website, YouTube also.
No. Don't worry. YouTube questions will be directly sent to you.
Okay.
You can
so I have to filter, right?
Yeah, they will send you. And then from there you can decide.
Okay. So I will filter the question. That is, which question is okay.
Okay.
So let's start with introducing Professor Weissman. So good morning to Indians and good afternoon to Professor Weissman. I'm Alok Kumar Pan and I'm the moderator of this session. And I thank Professor Panigrahi for giving me the opportunity to introduce Professor Weissman. And it is, of course, our great pleasure to have him with us. I think Professor Weissman needs no introduction to the PhD students and the faculties we have in our field. The name Weissman is enough. However, there are around 15,000 students registered. I mean, Professor Weissman may not see here in the Zoom, but in the YouTube channel, we have around 15,000 registered students. So I was looking at his CV and available online, and it is just 60 pages. So if I try to briefly summarize this CV, it will take an hour. So I shall just point out a few key important things. Professor Weissman, currently the director of Center for Quantum Dynamics at the Griffith University, Australia. And if I am not wrong, I'm surprised a little bit that he did his PhD with Professor Milburn in just 2 years. And he became professor at Griffith University when he is just 36. So apart from being in the editorial board of many high-valued, high-impact factor journals, he is actually the member of the fellow of many physical societies, including American Physical Society, Australian Physical Society, Optical Society of America, and many more. And he received quite a number of awards, including the Bragg Medal and the Australian Prime Minister Award in Science. And he has published around 250 research articles, and it will be surprised that is 75 of his H index is 75. That means the 75 articles has at least 75 citations. And importantly, around 60 of his publications are published in a high impact factor journal, including the Science, Nature, Nature Physics, Nature Communication, PRL. And in fact, he's maybe the best known for his work in quantum steering, but I think he has quite a number of pioneering contributions to our field in quantum foundations and quantum information theory. And his recent work, published this year, in the Heisenberg limit in laser coherence, that's one of the fundamental contributions. And he wanted to talk about on it, but I just requested him to talk in this Wigner-French paradox. And this work is, I think, it is one of the pioneering and the fundamental work in recent years. And it has already created a huge sensation in the worldwide community and across the world. So today we got the opportunity to listen this talk, this Wigner-French paradox from him. I think it's a huge opportunity for us, for the students, to ask directly the questions. And maybe if the students are very careful, that there are many students, the BSc and PSMA students, they may get a jackpot because they can get a chance to work with Professor Weissman at Griffith University. So with this, I would like to invite Professor Weissman to deliver his lecture. Thank you.
Thank you, Professor Pan. So should I do the screen sharing now?
Yeah, please share the screen.
Yes. How do I get that to work?
Yeah, it's perfect. Move on to slide. Let's see. Yeah, it's working.
It moves, yes. And do you see the mouse moving as well?
Yes, I can see the mouse as well.
Okay, that's great. All right. So thank you, Professor Pan, for that very flattering introduction, and thank you also to Professor Panikrai for the invitation. So it's a great pleasure to be talking at this summer school, and it's an extraordinary number of people that you have registered online. So that's a really great honor to be talking to so many people. And I see that you have a huge number of impressive speakers to come. So it's also an honor for me to be talking on the first day of what looks like a fantastic summer school that you have here. So, so what I'm going to talk about today is, so it is indeed about Vigner's friend, but that I won't get to that Vigner and his friend until a little way through the talk. So my title is just, can a qubit be your friend? But yes, the friend here is referring to Vigner's friend, as we'll get to. And the subtitle is why experimental metaphysics needs a quantum computer. And I'll explain what these things mean as we get along. Okay, as Professor Pan said, I'm at Griffith University, so that's at Brisbane and the Gold Coast here in Queensland, Australia. So I'm director of the Centre for Quantum Dynamics, which we have here. And the work that I'm talking about today is funded as well by external funds from the Centre for Quantum Computation and Communication Technology, which is an Australian Research Council Centre of Excellence, and also from the Foundational Questions Institute in the US. Okay, so indeed, the work I'm talking about has been recently published. It was in this paper just last year. And as you see, there are many other people involved in the work apart from me. They were all at Griffith University, so maybe I should point out, so this was a joint theory experiment paper. So Jeff Pride is the head of the lab where the experiment was done. The two corresponding authors are actually Nora Tischler, an experimentalist, and Eric Cavalcanti, who's a theory colleague of mine. And then we have PhD students, experiment and theory. And another postdoc, and Yongcheng Liang is at the National Chen Kuk University in Taiwan. He's the only non-Griffith author. Okay, so and this is some artwork done to illustrate this work. Unfortunately, it didn't get us onto the cover of Nature Physics, but it's a rather attractive piece of artwork anyway, illustrating this idea of Vigner's friend. And so what we have here is a new no-go theorem relating to Vigner's friend. So it's a theorem, which is something which the theorists obviously proved, and then which we illustrated by doing an experiment as well. And that's what I'll talk about as we go along. So that's going to be most of the talk. But then in the latter half of the talk, since I've got an hour, I should keep an eye on the time. I want to talk about some even more recent work, which is not even on the archive yet. So this is work in preparation. So by myself, by Eric Cavalcanti again, and by a colleague of ours, Eleanor Riefel, who's at the NASA Ames Quantum Artificial Intelligence Laboratory. Okay, and there's a picture to go with that as well, but I won't stop to explain all of that. All right, so here's an outline of my talk. So I'll begin with the background to the new work. So starting with the motivation for it, and then I want to explain the two historical pieces of work that underpin it, which is Bell's theorem and Vigner's thoughts about the mind-body problem, as we'll see. Then I'll present our new theorem and the new experiment which goes with it. And then, as I said in the last part, I want to go beyond what we talked about explicitly in that paper to talk about, what's the future of experiments in this area and what are the implications of those for interpretations of quantum mechanics. Okay, so motivation. So quantum computing, let's start with something which we've already heard a bit about. So Professor Powell talked already about the uses of a quantum computer. And so here are some examples. Why would we build a quantum computer? Who wants a quantum computer? Well, intelligence agencies are interested, hopefully for the good purpose of protecting us from bad people. Corporations are interested because it could make their businesses more efficient. Climate scientists and other modelers are interested because it could do modeling more efficiently, and that could help save the world. As Professor Powell talked a lot about, the applications in biology and chemistry and medicine, which are all really applications of chemistry, in improving materials, improving drugs, saving lives by those means, etc. Moving to some more abstract things, computer scientists are interested from a fundamental level because a quantum computer could disprove the so-called strong church Turing thesis, which is the idea that everything, every physical process at least, can be simulated efficiently by an ordinary computer, an ordinary classical computer, such as you're all watching this talk on. So that's a thesis which was popular in the mid-20th century, from the put forward by Church and Turing, two of the founders of the field of computer science. But now we have actually very good evidence already that this is just false. That there are things that a quantum device can do that cannot be simulated efficiently on an ordinary computer. So that's we can almost tick this goal off now. I think the evidence is so good with the experiments coming from Google and USTC. But then there's still much more to come after that. I mean, I think as a quantum physicist myself, I have to list what I think are the very interesting applications of quantum computing, which would be for advancing physics by allowing us to explore physical processes that we wouldn't otherwise be able to explore because it's just too difficult computationally on a conventional computer. And this could even go so far as theories that go beyond our knowledge, completely beyond our knowledge at the moment, such as quantum gravity, and trying to understand how that theory might work. Okay, so lots of people who would like to have a quantum computer for good reasons, but in this talk I am going to propose, or well, not as a brand new idea, but I'm going to talk about a different market of people, arguably a very small market, but nevertheless, I want to say that this would be a very interesting application for a quantum computer as a use for philosophers to advance this field of experimental metaphysics. Okay, so I think everybody here knows what an experiment is, and so they know what this word experimental means. But what about this word metaphysics? So here's a, why is it not working? There we go, whoops. Okay, here's a standard dictionary definition. Metaphysics, the branch of philosophy that deals with the first principles of things, including abstract concepts such as being, knowing, identity, time, and space. So basically, all the most fundamental things you can think of, that's what metaphysics is about. Okay, we don't need to go into the origins of it. Now, so metaphysics actually has a pretty bad reputation in science. So, for example, the Scottish Enlightenment philosopher David Hume said this about metaphysics. If we take in our hand any volume of divinity or school metaphysics, for instance, let us ask, does it contain any abstract reasoning concerning quantity or number? No. Does it contain any experimental reasoning concerning matter of fact and existence? No. Commit it then to the flames, for it can contain nothing but sophistry and illusion. Okay, so he was very down on metaphysics, thought of it in the same light as divinity. But the whole point of the field of experimental metaphysics is to change the answers of these questions. Okay, so experimental metaphysics is a term that was introduced by modern philosopher Abner Shumani, who died just recently, actually. And it was introduced in 1987 by him, and it's precisely about the idea that we can do abstract reasoning about metaphysics, and even further, we can subject it to experimental test. And that's the whole idea of experimental metaphysics. And so that way we can actually, I think, go beyond Hume's dismissal of it and embrace it as, in fact, a contribution of philosophy to science. Okay. So, as I said, this was a phrase that Shumani introduced in 1987, and you can see that by a poster for a conference 30 years on in 2017, Experimental Metaphysics 30 years on. And in fact, so Eric Cavalcanti is down here, was one of the speakers of that at that conference, although he wasn't speaking about this work because we hadn't done it at that stage. Okay, so the book where this phrase experimental metaphysics was introduced was this one here called Philosophical Consequences of Quantum Theory, subtitled Reflections on Bell's Theorem. And that tells you something important. It's that, Bell's theorem is really central to this idea of experimental metaphysics, and because it is in fact the first example of a theorem of experimental metaphysics, to use that phrase that Shumani introduced. So we're going to have to understand Bell's theorem. Okay, anybody could give a whole talk on Bell's theorem because it's very important and it's subtle, but unfortunately I have to get through it quickly to get onto the new work. So I encourage if you don't quite follow what I'm saying, there are many popular presentations of Bell's theorems, and some of them are good. Okay. All right, so I'm going to talk, so Bell's theorem was introduced by him in 1964 in this paper here called On the Einstein-Podolsky-Rosen Paradox. And there's Bell, okay, slightly later than this. But what he proved in this paper, which is a purely theoretical paper, is summed up by this paragraph from the conclusion. So he says, the statistical predictions of quantum mechanics, and I'll come back to why that's in brown in a minute. The statistical predictions of quantum mechanics are incompatible with separable predetermination. And then he clarifies, that is, in any theory in which parameters determine the results of individual measurements, there must be a mechanism whereby the setting of one measurement device can influence the reading of another instrument, however remote. Okay, so this first part, so here he says it's incompatible with separable predetermination, and then in the second part he's reiterating that. He's saying, so in other words, if you assume predetermination, if you assume that there are parameters which determine the results of individual measurements, then this other assumption, this separable type of assumption, must fail in that there must be this mechanism for non-local influence. Okay, so the brown here, this is because this is not actually, it is a theorem related to quantum theory, but the crucial thing is that it's not just a statement about the theory, it's about what the theory predicts and what we can rigorously derive or say, conclude, that's what I'm looking for, if those predictions are found to be true. Okay, so we don't actually need quantum theory to be true for Bell's theorem to be interesting. All we need is for it to be true enough that the statistical predictions can be observed to some level of accuracy in the laboratory. Okay, so ultimately it's a theorem about what we could observe experimentally and what that would mean. Okay, and so that's the sense in which it's a theorem of experimental metaphysics. Okay, so when Bell wrote this in 1964, these statistical predictions were merely statistical predictions, like nobody had done an experiment of the type that was relevant for his theorem. But that changed not long after. The first experiments started to be done in the 1970s, and they've been getting better and better. In particular, there are so-called loopholes which keep getting eliminated, to the point that it's now widely regarded that work done in 2015 has basically eliminated the loopholes. And so I was asked to write a little opinion piece in Nature about one of these experiments, so here the title I used, Death by Experiment for Local Realism. And so that was really exciting time, right? That 50 years after Bell's predictions, we can finally say that the definitives of the experiments realizing the statistical predictions of quantum mechanics in the relevant regime have been done. Okay, but one thing you might note is that, what exactly is it that these statistical predictions, or rather now these observations, what do they actually tell us? Because there are a lot of different words being used here. Like if we look up here, I use the word local, but Bell, in the quote that I showed you earlier, used the word separable and then used this description about a setting influencing a readout. And then this other part, which Bell called predetermination, but then he also talked about determining. And then we also see the word realism, which I used here. And there are other ways of expressing this as well. This can all be a bit confusing, okay? So what precisely are the metaphysical assumptions that lead to the contradiction with the experiment according to Bell's theorem? Well, there are actually many different ways to formulate that. But for the purpose of this talk, because it's going to be the most useful way for going on to the new work that I'll be talking about, the metaphysical assumptions are as follows, okay? So we can say that Bell experiments now, okay, because the experiments have been done, rule out the conjunction of these metaphysical assumptions. So number one, absoluteness of observations. That means that an observation is a real single event and not relative to anything or anyone. Okay, so those who know a bit about the interpretations of quantum mechanics might recognize that this is put here explicitly to refer to the types of things which are assumed in some of the weirder interpretations of quantum mechanics. So Bell did not ever write down, at least in his early papers, never explicitly wrote down anything about this, because it seemed like, well, of course you would assume that, right? It's just saying that when you do an experiment and you get an outcome, that's a real thing. Okay, you don't have to say anything more about that. There just is an outcome. If somebody else is doing an experiment at the same time, they also get an outcome, and there's nothing more to be said. Okay, so that's, but as we'll see, this will be important later. Okay, absoluteness. Number two, predetermination. So I'm going to use the same word that Bell used in 1964, predetermination of observable events. Now, this is actually surprisingly difficult to formulate completely rigorously. I'll read it out because hopefully we have time. For any observable event, capital A, and any event alpha in the past light cone of A, so I'm hoping that everybody here knows their relativity, but I'll have a picture in a minute. Any event in the past light cone of A, there is a space-like hypersurface, S, which basically you can just think of as a time-like sheet. Okay, so a constant time sheet in space-time containing this past event alpha, such that all events on, all events on or variables defined on S, this time, plus free choices subsequent to S, suffice to determine A. Okay, so if you thought that was pretty horrible and complicated, then I agree with you. Okay, that's what this little face is meant to represent. But don't worry too much about that, because this is the assumption that is we're not going to have to worry about for most of this talk. Okay, so we have it for the moment, but we're going to get rid of it, as we'll see. And third, an assumption, so I'm not going to call it separability or locality. I'm going to use this specific word, local action, which means this. Any free choice, X, made in a manner appropriate for a randomized experiment is, for the purpose of that experiment, correlated only with events in its future light cone. Okay, so it can't be correlated with events which are space-like separated. It can't be correlated with events which are in its past. It's a free choice for the purpose of this experiment. Okay, that's an important point to make. This is not saying that there might not be things, you know, that are correlated with the free choice that you make, for example, but it's just that for the purposes, pardon me, that for the purpose of the experiment, there's no reason to think that those are relevant. And so for the purpose of the experiment, we can assume that a free choice basically only has statistical consequences which would appear in correlations in its future. In other words, its future light cone. Okay, so for the experts out there, this term local action is not the same as local causality or locality as most people use it. And also to say that this assumption also rules out superdeterminism. So it actually does a lot, but it's not the same as local causality. All right. Right, how does this all work together? Okay, so this is a typical scenario for a Bell experiment. So this is a space-time diagram with space here, time here. So we have two parties, Alice and Bob. So Alice's lab is over here, which means that, you know, it stays in the same place and just goes up in time. And Bob's is over here, so the same thing over here. We have events, which are Alice choosing her setting, in other words, the way that she is going to make a measurement in her lab. And Bob similarly is going to make a setting choice over here in his lab. And then a bit later, after the setting choice, Alice gets a result A and Bob gets his result B. Okay, so the crucial thing in the way it's set up is that the future of this setting choice, this free choice X, is up here. These are light cones, these diagonal lines. So it does not include Bob's outcome, and likewise Bob's settings, the future of Bob's setting does not include Alice's outcome A. All right, so what that means is, well, let's have a look. Since we're talking about that, that means that the assumption of according to the assumption of local action, the probability of Alice's outcome. Oh, sorry, and I missed out, right? And then in the past, right, we have this space-like hypersurface, which I could have drawn as flat, okay, just being a fixed time, but just to make things more interestingly, it can be any curve as long as the slope of the curve isn't greater than diagonal. Right, and on that, there could be some hypothetical hidden variables, okay, as we call them, these other variables, lambda. They may be there, they may not be there, but let's just put them there for the moment and say they might have some role in this experiment. Okay, so you'll note that I haven't actually said anything about quantum mechanics yet, all right? And we're going to keep it that way for the moment. So these metaphysical assumptions, so the metaphysical assumption one is just that these events, you know, all exist they all exist in the same universe, if you like. We can talk about, for example, therefore, probabilities of outcome A and outcome B in the same mathematical expression because they just both exist. Okay? And likewise, X and Y both exist. All right. So local action, as I was saying before, the consequence of this Y being space-like separated from this A is that under the assumption of local action, that means that the probability of A conditioned on these hypothetical lambdas that may exist and conditioned on X and conditioned on Y does not actually depend on Y, okay? So that there is another probability distribution, just PA given lambda and X, which this is equal to for all Y. It doesn't matter what Bob chooses. And similarly, for Bob's outcome, it doesn't matter what Alice chooses. That's irrelevant to the probability, the outcome that he's going to get. And finally, local action also guarantees that the probability distribution for these hidden variables, whatever they might be, doesn't depend on the later settings X and Y, because this is all not in the future light cone of X and Y. Okay, so that's local action, is doing all that. And then predetermination is where the hidden variables actually do something. The assumption of predetermination is that with these hidden variables, which could be anything, right? But if we have predetermination, then we are going to have to include them, right? If we want to be as general as we can be about what might be causing things to happen in the world. Predetermination says that the probability of outcome A, given all the things that could be relevant, so that's lambda, X, and Y, okay, because we haven't applied local action yet, so it could be any of these things, right? The probability of that is either 0 or 1. Which just means to say that for a given A, right, it either happens or it doesn't happen. Like an outcome A equals +1, well, if it's predetermined, then either it is definitely going to happen or it's definitely not going to happen. So the probability of that will either be 0 or 1. And the same for the probability of B. Okay, so what we do in Bell's theorem is to take these constraints, these equations, and from them derive constraints on P of A, B given X, Y, okay? And the crucial thing here is that lambda does not appear in this expression, okay? So these are things that we can measure experimentally because this just involves only things which we actually control and observe. So we control X and Y and we observe A and B, and the hypothetical lambdas do not appear in this expression. Nevertheless, we can, by considering those, we can derive constraints on that, which are then violated in an experiment, okay, as we talked about before. So specifically, why is that not working? Okay, so specifically, I thought since people might not be familiar with it, the simplest example of a Bell experiment is where Alice and Bob each have a choice of 2 different measurements, which we'll call 1 and 2, and their outcomes there are 2 possible outcomes, +1 and -1 for each of those. And so these are exactly as before, just these equations for predetermination and local action. And as I said, what we can do is derive constraints on this. And the relation of this to the expression with lambda is that, actually that's wrong. There should be a P of lambda in that expression as well. Sorry, so we're averaging over the lambdas. So sorry about that. But when we do that and we put these constraints on the probability distributions with the A, B, X, Y, and lambda, we can derive an inequality like this one here, okay? So this is an inequality involving various probabilistic outcomes. So it's a sum over the possibilities of +1, -1 for A, B. We multiply those numbers together here. And this whole thing together, we can prove has to be less than or equal to 2. And this actual inequality is known as the CHSH, or Clauser-Horn-Shimony-Holt, and so that's the same Shimony who coined the term experimental metaphysics. And it was 1969 that they introduced this. It's a nicer form than the original inequality that Bell introduced. Okay, and then the crucial thing is that the predictions of quantum mechanics is that this can be as large as 2 times square root of 2. Okay, but the crucial thing for it's not necessary to reach 2 square root of 2 to disprove these assumptions. All we have to do is get bigger than 2. And so in the first loophole-free experiment, it didn't actually get terribly close to 2 root 2, but it saw a value of about 2.4, which is still well above 2. And so that's good enough to conclude that one of these assumptions must be wrong, okay? Because we just made these 3 assumptions, we derive this equation, and then we see experiments and violate that. So either absoluteness of observed events, predetermination of outcomes, or local action has to be false. Okay, and that's Bell's theorem in more time than I should have spent on it probably, but less time than I could have. All right. Okay, so the other crucial input to the new work is Wigner. Wigner's musings are the call it here. So this dates from roughly the same time as Bell's work, a few years earlier, and it's from a book called Remarks, or rather the essay I think is called Remarks on the Mind-Body Question. And really this is, yes, musings on the quantum measurement problem for those who have heard of that. But it's worth also reading what Wigner actually wrote in this paper. So he's fairly succinct on the point that we are going to take. So he says, so he's talking about quantum measurements, okay? And then he says, so first he just considers, well, I make a measurement on a system, all right. But what happens, he says, it's natural to ask about the situation if one does not make an observation oneself, but lets someone else carry it out. What is the wave function if my friend, and so this is where the friend is introduced, looked at the quantum object? The answer is that one can only attribute a wave function to the joint system of friend plus object. Oops, okay. And so this is the, whoops, where's my mouse gone? Uh-oh. Oop, there we go, right. Right, sorry. A joint system of friend plus object, which is this entangled state, for those who know about entangled states. Oh, and I really should have mentioned, sorry, that the way we actually do experiments that violate a Bell inequality is to share an entangled pair of particles between Alice's and Bob's lab. Okay, that's what we actually do. But I didn't put this in to just deliberately point out that the Bell's theorem doesn't rely on quantum mechanics being correct, that we don't have to use quantum mechanics to get the description here. We just have to say that, we get some predictions here, and if we violate it experimentally, then that proves that these predictions are, these assumptions must be wrong. But in practice, we do this by having an entangled pair of particles here. Okay, so sorry. Going back to Wigner, he's just considering a single particle, but then considering a friend measuring that particle, and basically says that what would happen according to quantum mechanics is that I'd end up with an entangled state of the friend and the particle. Yeah? So one could only attribute a wave function to the joint system of friend plus object, alpha psi times chi plus beta psi 2 times chi 2, psi 1, chi 1. And that this follows from the linearity of Schrodinger's equation. And he's quite right here, okay? If you just apply quantum mechanics, quite right. Obviously, a realistic description will involve more than just the friend and the object. It would involve the environment as well. But fundamentally, it's still the case that you end up with just a big entangled superposition according to Schrodinger's equation. And then he goes on and says, this appears absurd because it implies that my friend was in a state of suspended animation before he answered my question about what he saw. So what he's saying is that in this case, I'm not sure which one is the friend. Let's say that psi 1 is the friend. This means that the friend is actually in a superposition of, say, having seen the particle in state chi 1 and seeing the particle in state chi 2. And it's neither the case that the friend has seen one or the other. The friend is just in a superposition or a state of suspended animation, as Wigner called it, until Wigner asks the friend, what did you see? In which case the friend will either answer 1 or 2, and then the wave function would collapse according to at least some interpretations of quantum mechanics, that when Wigner looks at it, that's when the wave function would collapse. All right, but Wigner understandably thought that this was problematic because why should he, Wigner, be in any sort of superior situation than his friend? So what he concluded was that Schrodinger's equation cannot be linear. He just thought this is just wrong. This cannot be true. If it is accepted that my friend, who's in this superposition, has the same types of impressions and sensations as I. So in other words, Wigner thinks, if I collapse the wave function, then so must my friend. Okay, so it must just be wrong, that quantum mechanics must be wrong when applied to the friend because it says that the friend is in a superposition. Okay, so that is the infamous Wigner's friend, introduced in 1961. And what has happened in relatively recent years, and there's a couple of works that did this, but what I'm going to do is just concentrate on the one that was most relevant to our work. So that's this paper by Czeslaw Bruckner, published in 2018. So this is Czeslaw. This is, and the title of his paper was a no-go theorem for observer-independent facts. And his basic idea was to incorporate Wigner's friends into a Bell experiment. Okay, so to have, instead of just two particles which are entangled, have two particles, but then two friends as well, and then two extra people, Alice and Bob, to measure the friends. Okay, as we'll see pictures of in a minute. Now, unlike Wigner, so Wigner just thought that it would be absurd for friends to be in superpositions, but but Bruckner, to the contrary, assumes exactly that they can be put into superposition. So for Bruckner, the default prediction of quantum mechanics is in fact that friends can be put into superpositions and do not collapse the wave function. Now, why would you want to do this? Well, the big idea is to get rid of the assumption of predetermination in Bell's theorem. And the idea about how to do that is to make the friends observations, which are things that we, just assume because they're friends that they make observations, okay? Make those play the role of the hypothetical hidden variables which existed in Bell's theorem. Okay, which we have no reason to believe actually exist because that's purely hypothetical, right? So that would be that would seem like a great idea. Unfortunately, the way Bruckner actually formalized his theorem rather, is that he made metaphysical assumptions trying to implement this big idea, which meant that in the end, he didn't actually prove anything more than Bell had already proved. So his assumptions ended up being just as strong as Bell assumptions. And yeah, so it was a good idea, but it didn't actually prove anything new. But the good news, why is this not, there we go. The good news, right, is that we have found a new theorem, okay, which uses a much weaker formalization of the metaphysical assumptions that Bruckner was talking about. So in other words, we are able to prove a no-go theorem using much weaker assumptions than Bell. Okay. So let's get on with it, the theorem that we actually proved here. So this is the theorem then. Okay, can jump straight to it. That the conjunction of these assumptions is a contradiction. So number one is the same as before, absoluteness of observations. An observation is a real single event and not relative to anything or anyone. Assumption 3 is the same as before, local action. Any free choice is correlated only with events in its future light cone. Assumption number 2, you'll see that predetermination has just gone. We don't have an assumption of predetermination anymore. However, we have made an assumption, which I'm calling here for this talk, superpowers. Okay, we don't call this in the paper. And this is the assumption. So the reason it's called superpowers is that in the Wigner's friend scenario, Wigner is sometimes called a super observer. If the friend is an observer, then Wigner is above the friend. So Wigner is a super observer. So we say basically the super observer has superpowers. The super observer can perform arbitrary quantum operations on an observer, that is the friend, and the friend's environment. Okay. Now you'll see that I use different colors for this theorem because this assumption of superpowers is not a metaphysical assumption. Okay, so in terms of metaphysical assumptions, we are strictly making fewer assumptions than Bell because we just have this absoluteness and local action, and we do not have predetermination. Okay, we've lost that assumption, which most people thought was, the obvious assumption to give up anyway. Because, it seems like a very strong assumption. Why would the universe be have predetermined outcomes? Quantum mechanics, it's not true in quantum mechanics for a start. So it would seem to be like the obvious thing to give up. And so with Bell's theorem, that's what a lot of people just say. Well, okay, Bell's theorem doesn't worry me too much because predetermination is not something I believe in. So the importance of this theorem is that we don't use that assumption at all. We only use the much weaker assumptions. Well, I shouldn't say they're weaker assumptions. The other assumptions, and so because we don't have predetermination, overall the assumptions we're making are lesser than Bell made. Okay, but we have to make this assumption of superpowers, which, as I said, is not a metaphysical assumption, because this is something that can be tested experimentally. Okay, this is just saying something about what can be done in an experiment. Now, it may or may not be true, this assumption. Okay, but we're saying, and just as when Bell made his theorem in 1964, he did not know whether the predictions of quantum mechanics in a Bell scenario would actually come out to be the way they have come out to be, okay, the way that standard quantum mechanics predicts. But arguably, in exactly the same way, we could say that standard quantum mechanics says that this is true. There's nothing in standard quantum mechanics that forbids performing quantum operations on other observers. So the default assumption would be that this is true, but we're not going to say that it necessarily is true. It's just an assumption, but it's something that can be tested experimentally. Okay, so that's the situation. Okay, so how does this all work? Right, so as I said before, I mean, I should really have had a picture. With a Bell experiment, one has an entangled pair of particles between two laboratories. And here it's shared between the laboratory of Charlie and the laboratory of Debbie over here. But these Charlie and Debbie, they are observers, but they're not the super observers, okay? Okay, so they're observers because they make a measurement respectively on the state of the particle and get certain outcomes, which you call C and D. But then let's just looking at one side now. So now we have a super observer, Alice, for Charlie. So Alice, unlike Charlie, so Charlie and Debbie just make measurements in a fixed basis. They don't choose their measurements, they just make a particular type of measurement. Alice, on the other hand, makes a choice of measurement, which is, as in the Bell case, absolutely crucial for the theorem. So if Alice chooses her first setting, okay, that x equals 1, then she just asks Charlie what he saw. Okay, she, if you like, opens the laboratory containing Charlie and says, hey, Charlie, what result did you get? And Charlie reports his result C, and Alice writes that down as her result A. So whatever Charlie says, Alice just takes that as her result as well. On the other hand, if Alice, so that's either we have x equals 1 or we have x is not equal to 1. So in other words, in all other cases, if Alice chooses some other setting, what that corresponds to is that she, what she does is press a button which reverses time, unitarily reverses whatever happened in Charlie's lab, so that to begin with, Charlie has made a measurement, but after she's reversed time, then we're back to the situation where Charlie is not entangled or not correlated with this particle at all. Okay, so the particle is now here as if it had never been measured in the first place. Then Alice simply throws away Charlie and makes her own measurement on the particle in whichever basis she chooses, okay, depending on the choice she originally made. And thereby gets her outcome A. So that's how Alice gets her outcome A in these other cases where x is not equal to 1, as opposed to how she gets it in this case here. All right, and then so on the other side, the same thing's happening with Charlie and, with Debbie and Bob. And so what we have is a space-time diagram that looks something like this. So Charlie and Debbie have outcomes. Alice makes and Bob make setting choices, and then they interact with Charlie and Debbie respectively to get their outcomes. But things can be arranged in the same sort of space-like separated way, so that Bob's setting choice cannot influence Alice's outcomes, and likewise with Alice's setting choice and Bob's outcome. Okay. So in this case, so local action basically works much the way as before, except instead of the lambdas, C and D are playing the role of the hidden variables. Okay, so those are the real things that exist here, and local action applies to those outcomes. We don't have predetermination, as I said, so it's not that we assume that outcomes A and B are predetermined by things, okay? All we can say is that absoluteness means that C and D really exist, okay? They exist with A and B, so I can consider a joint distribution of A, B, C, and D, Okay, that's something that is sensible to consider because all of these are observed events. Absoluteness of observed events means I can consider them all in the same mathematical expression like this. So, as I said, we don't have predetermination, but we do have, except in the case that if Alice chooses her first setting, x equals 1, then her outcome is determined by whatever Charlie saw. And likewise, if Bob measures with setting 1, then his outcome is whatever Debbie saw. Okay, so there's predetermination only in that case, not predetermination in general. So it's not an exact map to the Bell assumptions or the way the maths work. But nevertheless, we have these assumptions, and just to be able to refer to these in a quick way, we call these the local friendliness assumptions. Okay, so for fairly obvious reasons, hopefully. Okay, so that's just a conjunction of those two metaphysical assumptions, and what we get is similarly to the Bell case, that these local friendliness assumptions imply constraints on just the P of A, B given X, Y. And so why do we only consider that? Well, because in some runs of the experiment, Charlie and Debbie's results, their outcomes get reversed, and so we never get to know what they are, and so we can't really test experimentally any expression which involves probabilities of those events, which we can't know at the same time as knowing A and B. So the constraints, the things that we can test experimentally, are only the probabilities of Alice and Bob's outcomes given their settings. Okay, but what we have from those assumptions before is constraints on this that can be violated, as I said, if these superpowers exist. But again, it's not that we have to assume that quantum mechanics perfectly describes the world, that it's possible to do perfect unitary reversals or anything like that. It just has to be similarly to the Bell case that the approximately, right, to some reasonable approximation, if I undo the Charlie's and Debbie's measurements, if Alice and Bob undo Charlie's and Debbie's measurements, then the probabilities, the results they observe, are approximately what they would have observed if there had been no Charlie and Debbie measurements in the first place, if they'd just been able to do measurements directly on the quantum particle before Charlie and Debbie got involved. Okay, so if this is the case, and it really only has to be a rough approximation for it to be good enough, then what we would see in the experiment would actually violate the constraints and prove that local friendliness is wrong. Okay, and so we have then a new theorem of experimental metaphysics because, right, it relates to experiment and it relates to metaphysical assumption, and it's a new theorem because the assumptions are different from those in Bell's theorem, and it's actually a stronger theorem. We don't have to say anything about predetermination. Okay. All right, so we did the experiment, and I could talk a lot about exactly like the theory behind the experiment, what we did in the experiment, what the results were, but I think I don't have time to do all that. If there are questions, these are some of the slides which I can use to answer your questions. But what I'm going to do is just jump straight to an experimental diagram. So this is how the experiment was performed. So it was performed like most Bell experiments with photons. So we have an entangled source of photons down here. So these are just things which collect the photons. So this is photon here, photon here. These are so-called polarization entangled photons. So that means there are correlations of an entangled sort between the polarization of this photon and this photon. Okay. Then it enters Charlie's lab here and Debbie's lab here. And then Charlie and Debbie make a measurement. Now, what is it for Charlie to make a measurement? Well, Charlie is actually just another, so I should say, a photon polarization, because there are only two perfectly distinguishable polarization states, like horizontal and vertical is a pair of distinguishable states. That means that a photon polarization degree of freedom is described as a qubit. Okay. Now, Charlie here is just another qubit, and this is another quantum degree of freedom which can have just two distinct values, two orthogonal states, which is the position of this photon. So the same photon, but we're treating its polarization degree of freedom as the system, and we're treating its position as a friend. Right? So Charlie's measurement of the polarization of the photon is just implemented by this polarizing beam splitter, which correlates the position of the photon with its polarizing. So this might be H over here, and whereas this would be B here. Okay. Now, if Alice chooses x equals 1, so if her choice of measurement is to simply ask Charlie what he saw, then what Alice does is put a mirror in here, which just sends the photon, if Charlie is in one state, to this detector, and if Charlie is in the other state, to this detector, and in this way, Alice finds out what Charlie saw. Okay, very directly. On the other hand, if Alice wants to do the other and measure with x equals 2 or 3 or something, what she does is logically reverse the measurement, which means using various other optical devices and then putting this state into another polarizing beam displacer, which reverses then the correlation or the entanglement, indeed, which was created by the first one. So that what comes out here is just exactly the same as what had gone here in the first place. So this is just a polarization qubit of the system. Charlie, in a sense, ceases to exist, okay? Or obviously the photon is somewhere, but that's independent, or rather uncorrelated with the polarization of the photon. Okay. And then Alice can just measure the polarization of the photon in whatever basis she likes, and that's what she's doing here. And then similarly with Bob and Debbie on the other side, okay? So that's how we implemented the friends and the measurements. And what we do is demonstrate a violation of one of the local friendliness inequalities, which we derive by many, many standard deviations. Okay, so in other words, we have very convincing experimental evidence of the violation of the local friendliness inequality. Okay, so I know from experience giving this talk is that even after I've described that experiment, a lot of people are confused and say, well, hang on, where was the friend? Where was the measurement of the friend? Okay. So I want to emphasize again here that in our experiment, the friend here is just another qubit, right? This binary degree, this path degree of freedom of a single photon, a single quantum particle, which is a photon. Okay. So it's a very simple type of friend. Okay. So this leads to the question, can a qubit be your friend? Okay. How, or put it this way, how can a qubit be a friend? And didn't you say that you needed superpowers to do a local friendliness experiment? Well, okay, in our paper, we're very clear that obviously a qubit is not a real macroscopic friend. Okay, and that's why we can do the experiment without superpowers. I mean, the experimentalists are very skilled on everything, right? They need a lot of powers, but they're not actually superpowers to do this experiment. So we're clear in our paper that we're not doing a genuine bigness friend experiment. We're doing a microscopic proof of principle version of such an experiment. Okay. Now, some of you might know that there's been other papers recently, which were, well, in particular, there was this paper, which was based on Bruckner's original theorem, okay, the one that didn't quite, wasn't ideal, let's put it that way. And in that one, it was very similar in that they also used a qubit as their observer or bigness friend, and they claimed that it was a genuine bigness friend. So all I want to say is that, yes, in that paper, they do say that, but we do not say that in our paper. Okay. All right. So if that's I'm going to have to go very quickly, I know, through this last part. So if that's not a genuine experiment that we did, what would one do to go beyond the toy experiment? What would make a convincing friend or convincing observation? So is it encoding information in a simple quantum system? Well, as I said, our perspective on that is no, okay? Well, at least my perspective on that is no. That's not enough. Okay, well, what about if we make it a much larger or more complex quantum system? Well, that's certainly an interesting direction to go experimentally, but there are numerous different criteria of what makes a quantum system large or complex, and there are no obvious thresholds to say, well, this is large enough or complex enough or whatever. I mean, one could always ask for more. It's not clear what one would really be aiming for. Now, an obvious question you might say about what is an observation would be, well, let's just go back to the founders of quantum mechanics. What did Bohr say an observation was? He said it was an irreversible act of amplification. Okay, well, that's a good answer, but that is not going to work for the experiment we want to do, because we explicitly want to reverse the observation. Okay, so if that's your definition of observation, then it's by definition impossible to do this type of experiment. And that would seem to be going too far to just rule out and say, well, it's just an impossible thing to do, because there are things that we can consider as friends that really seem very much like friends. And this was really Wigner's point, is that what if it is a being with the same types of impressions and sensations as I, in other words, as Wigner, you were saying. And I think if we do that, I think that's the best option. And it really would be hard to dispute that that was a genuine Wigner's friend experiment. But how could we do this? How could we do an experiment which involved unitarily reversing the evolution of a sentient observer? And well, the answer, this is where we come down to why experimental metaphysics needs a quantum computer, because that's how you would have to implement the friend. The friend would have to be an artificial intelligence running on an enormous fault-tolerant quantum computer. Now, you might still ask, how would we know that this device was sentient? Well, I think my take on that is that it's like Turing's idea about how we tell something is intelligent. You talk to it, okay? You engage it in conversation, and if it behaves like any human with a human level of intelligence, if it's capable of being your friend, then we treat it as a friend, okay? We treat it as something which can make, which has the same types of impressions and sensations as Wigner said. Okay, so as I said, that's my take on where we need to go experimentally. I think I'll have to skip through some of the remaining slides. So so the idea is that in this case, Charlie is just a quantum computer like this. So the measurement of Charlie of a qubit is just Charlie incorporating that qubit into his matrix of qubits, right? Processing it, right? Producing some huge entangled state, which we could think of as being Charlie thinking about what he observed. If Alice wants to know what Charlie observes, she hooks Charlie up to an output and asks him, and he tells her. But if she doesn't, right, if she wants to do one of the other choices, she simply does a unitary reversal of all the gates that have happened on Charlie since the measurement happened. That takes Charlie back to this state of being unentangled. And again, Alice can throw Charlie away and make her own measurement on the qubit as before. Okay, so there's a whole lot of things you could ask about the practicalities of an experiment like this. It's not going to happen anytime soon. This would be a very long-term proposal for an experiment, but it's something which we are working on, trying to come up with estimates for how difficult it would be. There are ethical issues as well, so I won't go into all of those. There are other ways. We don't really want to write down a theorem in terms of superpowers. That's another issue we don't want to do. We want to be realistic, and so instead of just talking about superpowers, essentially what we have is assumptions that human-level artificial intelligence is possible, okay? That we don't know for sure, although many people think it is, but it's not actually known for sure. So this is an experimentally open question. And then the other experimentally open question is that we can do universal quantum computing on an extremely large scale and also very fast if we wanted to react like a human. Okay. There are other things. I've also changed the way the metaphysical assumptions are set out, but unfortunately I don't have time to go through that. I'll just say the reason for doing it this way is to try to make a more direct connection with various interpretations of quantum mechanics. And so I definitely don't have time to go through this, just to say that there are many different interpretations of quantum mechanics, and they all give up something different in order to conform. If they're good interpretations, then they should cope with the theorem, but they can do that in different ways. But just to say that the no interpretation, which some famous physicists have said that quantum theory needs no interpretation, I think just fails according to this theorem. Okay, we can rule out the idea that we don't need to interpret quantum mechanics. We absolutely need to get to grips with really deep questions about what quantum theory is saying about the nature of the world in order to be able to understand how it is that this theorem of ours is compatible with our theories of the world. So I think that's the most interesting conclusion which we get to, is that you have to interpret quantum mechanics to make sense of this theorem. And arguably that's not the case with Bell's theorem. I mean, I think like a standard Copenhagen interpretation can just say, oh, well, we don't have predetermination, therefore we're not worried about Bell's theorem. That just doesn't work with our theorem. Okay, so take-home messages. So metaphysical assumptions that individually would not be testable can be testable in conjunction, because they have consequences that can be falsified experimentally. And in the case of the metaphysical assumptions that Bell used, we can say that they have been falsified, the consequences of those assumptions. What I talked about beyond Bell's theorem is the idea that continued advances in artificial intelligence and quantum computing, and I didn't much talk about it, quantum communications, will open up a new frontier in experimental metaphysics. And in particular, we could rule out these new conjunction of metaphysical assumptions, which I didn't get a chance to talk about, but I think you all have a basic idea. It's the local friendliness assumptions. And as I talked about, we have performed a proof of concept experiment in this area already. Okay, with that, I will end, and I'm very happy to take questions. Should I stop sharing, or should I maybe leave the sharing up, I guess?
Just keep it.
Yeah, okay.
So thank you very much for this excellent talk. And we have quite a number of questions. I mean, those who are in the Zoom, they can directly ask questions when I tell. And one more thing is I want to tell you, that is, you don't use any cryptic name, because someone wrote the cryptographic 161. You just use...
Sorry?
No, not to you. It's not to you.
Not to me? All right. Okay,
yeah. So, Annesa Pradhan, do you want to ask the question directly? Annesa? No. Okay, so he's asking that if the result of an experiment is dependent on the observer's system, can our existing knowledge and belief system affect the outcome, hypothetically?
Okay, so this is a question from YouTube or something, or is it?
It is a question from student. Should I repeat?
Yeah, maybe repeat, yes.
Yeah. If the result of an experiment is dependent on the observer system, can our existing knowledge and belief affect the outcome, hypothetically?
Okay, well, hypothetically, yes, you'd have to say yes. But also to say that there's no evidence experimentally that this is the case. So, I mean, people have obviously tried looking for evidence that our thoughts can affect the frequency of certain outcomes. So, for example, if you look at a quantum system being measured and think really hard about getting the +1 outcome more than the -1 outcome, can you influence the probabilities for that? And no experiment has shown any evidence for that effect. So so the link between observation and there are different interpretations. In some interpretations, there is, where are we? So there are some interpretations, such as Wigner's, for example. So maybe I'll use this here. Okay, so Wigner had the idea that consciousness, seemed to be saying that consciousness has to collapse the wave function, but that doesn't imply that it has to do it in anything other than a purely random way. On the other hand, Roger Penrose, so this is another interpretation which I discuss here. Roger Penrose really seems to believe that the way consciousness interacts with the wave function in order to collapse it is not purely random, but is rather is non-computable, and that this is somehow related to human intuition or the feeling of free will and all of these sorts of things. So maybe I would just say that there are serious scientists, Nobel laureates, who do think that there is some non-trivial relation between consciousness and collapse. Yeah.
There is one question from Aniket Kassav. What does the existence or the absence of non-local phenomena imply about the fundamental structure of space-time?
Yeah, that's a really good question. So some people think that Bell's theorem is enough, because there are other ways of formulating Bell's theorem which make it more plausible that locality is or local action is or something like that is what has to be given up. And that's deeply puzzling if one, and I guess what I should say is, if you think that about Bell's theorem, then you should think that even more strongly about our theorem, because in our theorem, we don't make this assumption of predetermination, which is usually what people say is the thing to give up instead of local action. But there are certainly interpretations which do give up local action, and so hidden variables interpretation, like Bohm, for example, violates this assumption of local action, and that is so that's a nice way to resolve the theorems, but it's deeply puzzling because all of the evidence we have about space-time is that the distinction between future light cones and past light cones and elsewhere is very fundamental to the universe, and yet these theories postulate that that influences happen faster than light all over the place. It's just that we can't use them to signal faster than light. And so this is very puzzling, that we would have a situation where there are all of these faster than light effects happening, but we can never use them to actually send a signal faster than light. So it's not to say that those theories are wrong or inconsistent or incoherent or anything like that, but it is, I would say definitely that it's deeply puzzling. But then I think any interpretation of quantum mechanics is actually pretty puzzling when you get into the details. That's my opinion anyway. So I don't have a simple answer, just to say that it is. I believe it's definitely a difficult problem to wrestle with. Yeah.
Thank you. There's one question from Sumit Mukherjee. He's asking that how can qubit represent a conscious observer when qubits themselves need to be measured with a conscious mind?
Yeah, so this comes back to the experiment. So maybe I should be even more clear. Okay, when I have the title, "Can a qubit be your friend?" My answer is no. Okay, so I am not claiming that the qubit is a real friend in this experiment. So this is not a real Wigner's friend experiment. This is, as we said, a microscopic proof of principle version. So it's more than just Bell's theorem again, because we are taking we are taking a quantum system here and we are entangling with another quantum system in such a way that if we choose, we can unentangle it, and we use this to make different measurements in different cases and look at inequalities. Pardon me. that are different from the inequalities in Bell's theorem, etc. Okay. But yes, does that mean that it's a genuine Wigner's friend experiment? No, because, right, I don't think a qubit can have consciousness, okay? But if I have quadrillions of qubits, or trillions of qubits, and they're running an artificial intelligence program, and they can have a conversation with you about any topic that you choose to have a conversation about, and they seem to behave more or less the same way that a human would, are you still going to say, oh, well, that's not a friend because it's just made of qubits? That seems to be, to use the language that we were on the paper that we're working on, is that's just not being friendly. Okay, that's violating this assumption of friendliness, which is basically to say we will treat if another party seems to be on the same level cognitively as me, then I will treat its thoughts to have the same level of reality as my own thoughts. Okay. Hopefully that answered the question.
Thank you. So you have many questions. One question maybe the students' interest. Maybe it's not directly related to it. That does the violation of Bell inequality violates or eliminates all kind of hidden variable theories?
Okay, well that's an easy question. Does the violation of Bell inequalities eliminate all hidden variable theories? No, it only eliminates local hidden variable theories. And so the example, again, come back to this example of the hidden variable theories of Bohm is not eliminated by Bell's theorem because it is a theory which explicitly violates this assumption of local action. And so it's a theory with predetermination, but it violates local action, and so it can get around Bell's theorem. It basically postulates that there are faster than light influences, as I was saying before. So no, there is no theorem that just rules out hidden variable. There is no, yes, they all have to make additional assumptions about those hidden variables. Yeah.
Okay, thank you. Let's say one question, that's what exactly the difference between locality, local causality, and local action?
Whoa, okay, all right. So locality itself is problematic because people use that word to mean different things. Okay, so maybe I will leave locality aside. Okay. Local causality is a stronger assumption than a much stronger assumption than local action. Okay, so basically Bell's theorem can be proven just assuming local causality, some sort of no superdeterminism, and the absoluteness of observation. So basically, if you assume local causality, you don't need predetermination because so let's see how to explain it. So predetermination and local action, say, together more or less imply that there are causes of an event in any observable event has causes in its past light cone which determine that event, determine that outcome. Now, local causality is a similar thing, but instead of saying that it determines that outcome, it just says that they determine the probability of that outcome, more or less. So essentially, local causality is like local predetermination, but allows for randomness, local randomness to exist as well. So it says that, well, it could be that just when the measurement is made, that some irreducibly random thing happens, but that's a totally local type of randomness. It affects the result here, but it doesn't affect the result anywhere else. So local causality is really as I said, so it's similar to local predetermination as Bell originally talked about, but it's slightly more general. Okay, whereas local action, as I've talked about, doesn't really talk about observable events and their probabilities or their determination or whatever at all. It just talks that it just says that a free choice is not correlated with anything except what's in its future likelihood. Okay, so that's so it says that if there's some observable event which is outside the future likelihood of my free choice here, then I don't influence it. But it doesn't say anything about any other events that could influence that observation. Okay? It doesn't say anything else about what might determine or cause that observation. I hope that makes the distinction clear. I'll make one more statement. I mean, yeah. So in Bell's original paper, 1964, where he uses the term locality, I would say that he uses it in a sense which is much closer to local action than it is to local causality. Okay, so it makes sense that in Bell's 1964 paper, you need the assumption of, as Bell put it, actually he called it, well, he used different words in different places in the paper, but he sometimes called it locality, sometimes called it separable, as we've seen. But basically, the type of assumption he was talking about there was similar to this local action, as opposed to local causality, which is more similar to a combination of these two assumptions here.
Thank you. So one question from Sagar Modo. Why do you need to have the knowledge about the metaphysical interpretation to learn quantum computing?
Okay, I never claimed that you need to have knowledge of metaphysical assumptions to learn quantum computing. So let's go back to my motivation. My motivation was, why would we want to build a quantum computer? Okay, so not how would we build a quantum computer? Okay, so none of these motivations tell you how to build a quantum computer. This is all just about why we would want one, okay? And obviously, most of these are going to have there's a lot more stake in a lot of these than there are in this one down the bottom. So essentially, my hope would be that we will build very, very large-scale quantum computers to solve all of these practical problems. And at the same time, we will develop artificial intelligence because there are so many applications of those. And then sometime down the track, in decades to come, we will be at the stage where we can put those technologies together and do the type of experiment that I talked about. Okay, so in a sense, I believe that we will get that experiment for free just because we're going to be developing these technologies anyway. So yes, so the answer to the question is you don't, right? But to address the more broad question about, is this a real motivation for quantum computing? Well, for me, it's a real motivation. I would really like to see this, but it's as I said, I think it's something which will happen for free down the track because of other reasons for wanting to build a very large quantum computer.
Okay, thank you. There is one more question from YouTube. How perfectly can the reversal of the Friend's measurement be realized in the laboratory?
Okay, so that's, so how perfectly can the reversal of the Friend's, the reversal of the Friend's measurement be done in the laboratory? Now, for a, for a real friend, that's a question to be answered. I mean, it's possible, of course, that Wigner is right, and that actually once you build a human level artificial intelligence, that it will actually collapse the wave function, in which case the answer is that it actually can't be reversed at all. So that's something we could really learn from doing this experiment with a real friend, okay? We could find that it is just not possible to reverse, that in other words, the quantum mechanics actually breaks down. Standard quantum mechanics breaks down. We can't do that reversal. But if you mean for the toy experiment which we did, how well were we able to do it there? So here I can get to now then. Does this, actually, can I interpret that from here? Ooh, I guess I don't. Yes, so now I'm not sure because I don't know exactly, can't remember exactly what these theory lines are. Yes. Okay. So I can't remember whether these theory lines are what would happen if everything was perfect. In which case you could look at that and say, well, we did very, very close to perfect. But it might be that these theory lines actually include the small amounts of experimental imperfections. So sorry about that. I can't answer your question directly. But just to say that we were able to do it. I mean, I do know from the experiment that we could do it very well. So, like with fidelities in the high 90%. And so it was not difficult in the sense to violate these inequalities once the experiment was built, because the laboratory of Jeff Pride is a very good laboratory for quantum optics. So in a sense, to see something interesting, what we actually did in the experiment was deliberately introduce noise. So that's what this parameter here is, just to show that different inequalities were more or less robust to noise. So that's really what this experiment results. So sorry that that's not a direct answer to your question, but it was to a very high accuracy in the experiment. Yeah.
Thank you. So one more question from Divita Gautam. Is there any interpretation of quantum mechanics where quantum entanglement is not considered to be the fundamental?
Yeah, that's a good question. I guess it depends what you mean by fundamental. I mean, so there are interpretations. Okay, maybe I'll start with one thing. So Einstein, for example, thought that entanglement was not fundamental. He thought that it was just a description, but that there would be a deeper description in which, there wasn't entanglement. He thought that there was something wrong with the way we were doing quantum mechanics because we had to deal with its entanglement, and that there would actually be just some local way of describing things. Okay, so you could say Einstein's interpretation, but the problem is that Einstein's interpretation fails. Okay, it's not a potential interpretation anymore because of Bell's theorem. We know that that's just out of the question. What Einstein wanted just cannot be. Okay, so in terms of interpretations that people still take seriously, even that we know about Bell's theorem and this theorem, I mean, I guess I could say that there are theories like cubism which don't deny that entanglement is part of the mathematical description we have to use, but which would say that it's not that it describes something out there in the world. They would say that it just describes what we expect to happen when we make measurements, and don't, in some ways, sort of similar to what Bohr might have said, just don't ask about what's out there in the world. We can't describe it. We know what the mathematics is to make predictions, but don't try to think about, what the quantum world actually is. So that's, I think, the only sense in which there are interpretations where you might say that entanglement is not fundamental, but just in the sense of that they would say that don't think of it as something real, just think of it as a mathematical device, but that's all we have. We only have mathematical devices. There is nothing else. There is nothing else out there that will ever take their place. I hope that was a fair representation.
Thank you. There's one more question from Asutosh Rai. Question is similar to Bell's theorem. Are the new constant of observable statistics due to the weaker assumption in Wigner-Friend scenario can also be considered independent of quantum mechanics?
Yes. So the question is, is this new theorem of ours, like Bell's theorem, are the inequalities which we derive independent of quantum mechanics? And yes, the answer is yes. And so that's why we call it a theorem of experimental metaphysics, okay? Because the inequalities we derive, going back to, right? So the inequalities we derive follow only from these equations here, okay? And these equations say nothing about quantum mechanics, okay? We are simply assuming that that Charlie and Debbie make measurements, and when we ask them the outcome, then that's what we write down, et cetera, okay? So the quantum mechanics only comes into it when we make the prediction that we think we can violate these inequalities in an experiment. And that's what we do. So that's why okay, maybe that's good enough. So yes, it's only when it's only this assumption here. So quantum mechanics does come into this assumption in the sense that it's saying we think that if quantum mechanics is universally valid, then we should be able to reverse the friend's measurements, and therefore we should get statistics after the reversal which are similar to the statistics if the measurements had never taken place. So that is using quantum mechanics, but as I said, we don't have to assume that to derive the inequalities. This is just what we assume to make the statement that we expect to be able to violate these inequalities in an experiment, but we don't know, as I said before. Like just as in Bell's case, in 1964, he didn't know whether the inequalities will be violated or not. So it's exactly the same situation in that respect.
Okay, thank you. One more question from students, that is, to justify superposition principle, can you say that the past, present, and future exist simultaneously?
To justify the superposition principle, I'm not quite sure how to answer that question, but I guess I would say that I didn't really include them in my list of interpretations, but there are interpretations which respond to Bell's theorem by thinking about the possibility of action not only being faster than light, but actually going backwards in time. So there are various people who work on approaches called retrocausal approaches, which try to think about what it would mean for a universe where essentially where causes don't just go in one direction of time, but they can go forwards and backwards. And so somehow all of space-time has to be sort of set somehow all at once because the future could influence the past. And then the challenge is to say, why would that lead to the quantum mechanical predictions which we see? Okay, so if you want to put it that way, what does it have to do with superposition? And I think that's an even bigger challenge than the challenge of trying to make sense of non-local theories like Bohm. Because we can see in a theory like Bohm exactly how quantum mechanical predictions arise. Whereas in the retrocausal theories, I think it's fair to say that there is no actual specific theory which has been proposed from which you can derive all of quantum mechanical predictions. I think there are toy theories which say, well, if you look at this particular situation, here is a way it might work here. But it's not as if it's a well-developed interpretation in the way that Bohmian mechanics is, for example. So that's really why I didn't include it in this table, because I don't think it's really well-developed enough to talk about how it would react to this theorem.
Thank you. And we have actually quite a number of questions, and I think Professor Panigrahi, so it's 1:30.
Yeah, I think we can probably call it a day, and then so those questions can be sent to Professor Wiseman if he doesn't mind later.
Sure. No, I won't promise to answer everyone necessarily individually, but but certainly if you send them to me and then I can reply to you and you can I guess that sounds like a good way to proceed.
Okay. So thank you very much once again for this excellent talk and the discussions.
Yeah, truly enjoyed your talk, Professor Weisman.
Thank you very much. It was a pleasure, and it's I'm really happy with the with the number of questions that it seemed to have provoked. So that's very good to hear. Okay, and I wish you all well with the future coming talks.
Thank you. Same to you.
So Alok, back.
Sorry?
We'll now.
Yeah, at 3. Yeah. I'll come back after lunch.
Yeah. So 250 kind of thing, huh?
250. Okay. 250. Sure.
And you will introduce
again. Okay.
Yeah.
That will be on weak measurement.
Something. Yeah. Sure.
Alok, that will be on weak measurement.
That will be on weak measurement. I think Fabrice will be talking on weak measurement.
All experiment. Yeah.